Tonight, we're going to explore a question that sounds simple but leads to one of the most profound revelations about the universe we live in. How many black holes are in the universe? You've probably heard about black holes before. Scientists talk about them constantly, these mysterious objects that devour light itself. But here's what most people don't realize. When astronomers actually tried to answer this question, when they calculated the real number of black holes surrounding us, they discovered something that changes everything we thought we knew about reality. The universe isn't mostly empty space dotted with stars. It's a graveyard, a vast cosmic cemetery filled with 40 quintillion invisible remnants of dead stars. That's more black holes than there are grains of sand on every beach on Earth, and they represent about 1% of all ordinary matter in existence, drifting silently through space, completely invisible to our eyes. By the end of this journey, you're going to understand how scientists calculated this staggering number and why it means we're living in a universe that's fundamentally different from what we see when we look up at night. Before we dive in, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now let's begin. Picture yourself on a clear evening, perhaps stepping outside after dinner, away from the glow of indoor lights. You tilt your head back and let your eyes adjust to the darkness. Slowly, the familiar tapestry emerges. A few dozen stars at first, then hundreds, then thousands as your vision sharpens. The Big Dipper hanging steady in the north, Orion striding across winter skies, or the summer triangle marking warm nights. These are the companions of human civilization, the same patterns that guided ancient navigators and inspired countless generations to wonder about their place in the cosmos. But as you stand there in that peaceful moment, absorbing the gentle light from distant suns, you are witnessing something profound without realizing it. You are looking at the visible minority of a much larger story. Those stars, beautiful and numerous as they seem, represent only a fraction of what actually surrounds you. The night sky you see is like the tip of an iceberg, revealing perhaps 1% of the cosmic inventory that fills the space between Earth and the edge of the observable universe. The rest remains hidden, not because it is too far away or too faint, but because it produces no light at all. This is one of the most remarkable discoveries of modern astronomy, and it challenges something fundamental about how we have always understood the universe. For thousands of years, astronomy was necessarily the study of light. Ancient stargazers tracked the movements of bright objects against the dark backdrop of space. Early telescopes gathered more light, revealing fainter stars and distant galaxies. Even today, our most powerful instruments are essentially sophisticated light collectors, designed to capture photons that have traveled millions or billions of years to reach us. We built our entire picture of the cosmos around what glows, what shines, what announces itself through electromagnetic radiation. Yet nature, as it turns out, does not share our dependency on light. Much of what exists in the universe produces no visible signature at all. It neither glows with internal fusion like stars, nor reflects light like planets and moons. It does not emit radio waves or X-rays or any other form of electromagnetic signal that our instruments can detect directly. These objects are gravitationally real, possessing mass and influence, but they remain completely invisible to traditional astronomical observation. They are the hidden majority, the dark foundation upon which our bright, observable universe rests. When we ask the question, how many black holes are in the universe, we are really asking something much deeper about the nature of reality itself. We are asking whether the universe we can see represents the universe that actually exists. We are questioning our fundamental assumptions about cosmic demographics, about the relationship between light and substance, about the reliability of our senses as guides to understanding the whole. This is not merely a counting exercise, though counting is involved. It is an investigation into whether our perception of the cosmos as a mostly empty stage, decorated with occasional brilliant performances by stars and galaxies, is accurate, or whether we have been systematically misled by our reliance on vision. The question also touches something philosophical about human knowledge and limitation. How do you count something that cannot be seen? How do you estimate the population of objects that produce no signal, leave no trace in traditional telescopes, and announce their presence only through the most subtle gravitational effects? The challenge seems almost impossible at first consideration. It would be like trying to count all the people in a vast dark room when you can only hear the occasional whisper or footstep, and most inhabitants remain completely silent. But this is exactly what modern astrophysics has learned to do, and the methods are as elegant as they are indirect. Rather than trying to spot individual black holes scattered across the cosmos, scientists have developed ways to understand how these objects form, how many should exist based on the life cycles of stars, and how their population should have grown and evolved over the entire 13.8 billion year history of the observable universe. It is detective work on a cosmic scale, using clues from stellar evolution, gravitational wave astronomy, and computer simulations that can follow the births and deaths of trillions of stars across billions of years. The answer that emerges from this investigation is both precise and astonishing. Current estimates suggest that approximately 40 quintillion stellar mass black holes exist within the observable universe today. That number, 40 quintillion, translates to roughly 4 followed by 19 zeros, a quantity so large that it strains human comprehension. To put this in perspective, it means there are more black holes in the observable universe than there are grains of sand on all the beaches of Earth, more than all the stars currently shining in all the galaxies we can observe, more than the number of seconds that have passed since the universe began. But the truly remarkable aspect of this number is not just its size, but what it represents about the fundamental composition of reality. These 40 quintillion black holes collectively contain approximately 1% of all ordinary matter in the observable universe. Not 1% of all matter, which includes the mysterious dark matter that makes up most of the cosmic mass budget, but 1% of the familiar protons and neutrons that constitute atoms, planets, stars, and everything we recognize as normal substance. 1% might not sound like much, but in cosmic terms, it represents a staggering repository of mass that remains completely invisible to our eyes and our instruments. This revelation invites you to reconsider that peaceful moment of stargazing with which we began. As you stand under the night sky, appreciating the gentle light from distant stars, you are actually surrounded by a vast, invisible population of cosmic remnants. They drift silently through space, each one the compressed core of a star that once burned brightly, lived its full nuclear life, and then collapsed into a gravitational well so deep that not even light can escape. They are the universe's way of preserving the memory of its stellar past, maintaining a dark archive of everything that has lived and died among the stars. Tonight, we embark on the journey to understand how scientists arrived at this extraordinary number and what it means for our place in a universe that is far stranger, far more populous, and far more hidden than the serene night sky suggests. When we speak of counting black holes in the universe, we must first be precise about what we mean by the universe itself. This might seem like an obvious concept, but in astronomy and cosmology, the word carries a specific technical meaning that differs from our everyday understanding. In casual conversation, when we say universe, we often mean everything that exists, the totality of all reality, infinite space extending in all directions without boundary or limit. But science operates within more modest and measurable boundaries. When astronomers count objects or survey cosmic populations, they work within what we call the observable universe, a finite region of space that represents everything we can, in principle, detect and study. The observable universe is not an arbitrary limitation imposed by our instruments or our imagination. It emerges from fundamental physics, specifically from the finite speed of light combined with the finite age of the cosmos. Light travels at approximately 300,000 kilometers per second, a speed that seems instantaneous in our everyday experience, but becomes a crucial constraint when we consider cosmic distances. When you look at any object in space, you are not seeing it as it exists now, but as it existed when the light left its surface and began the journey to your eyes. The sun, for instance, appears to you as it was 8 minutes ago. The nearest star beyond our solar system shows you its condition from over 4 years in the past. This effect becomes more dramatic as we look deeper into space. Distant galaxies appear to us as they were millions or billions of years ago, their light having travelled across the expanding cosmos for eons before reaching our telescopes. Eventually, we encounter a natural boundary. Since the universe is approximately 13.8 billion years old, we cannot observe anything whose light has been travelling for longer than 13.8 billion years. Beyond that horizon, signals simply have not had time to reach us since the beginning of cosmic time. But here lies a subtlety that often confuses even scientifically educated audiences. The observable universe is not 13.8 billion light-years in radius. It is much larger, approximately 46 billion light-years in radius, making it roughly 93 billion light-years across. This seeming contradiction between age and size arises from a fundamental property of space-time itself, the expansion of the universe. When we say the universe is expanding, we do not mean that galaxies are simply flying apart through static space, like debris from an explosion moving through an empty room. Instead, space itself is stretching, carrying distant galaxies away from us as new distance appears between existing points. This expansion has been ongoing throughout cosmic history, which means that a galaxy whose light left it 13 billion years ago has moved much farther away during the time its photons were travelling toward us. The light we receive today from the most distant observable objects began its journey when those sources were only a few billion light-years away, but they now reside at distances approaching 46 billion light-years. This expansion also explains why the observable universe grows larger every day, not just because time passes and new light arrives, but because the cosmic horizon itself moves outward. Objects that were once beyond our observational reach gradually come into view as their ancient light finally completes its extended journey through expanding space. In a sense, the observable universe is like a growing sphere centered on Earth, its boundary constantly pushing farther into the depths of space as more of the cosmos becomes accessible to our observation. The practical consequence of this boundary is profound for any cosmic census. When we ask how many black holes exist in the universe, we are necessarily asking how many exist within this observable sphere. We cannot count what lies beyond the horizon, because no information from those regions has reached us. We cannot even confirm that the same physical laws apply in unobservable regions, though we generally assume they do based on the principle that the universe appears broadly uniform on large scales wherever we can see it. This limitation might initially seem frustrating, as if we are trying to understand an ocean by examining only a single drop. But the observable universe is hardly small or unrepresentative. It contains at least 2 trillion galaxies, each hosting billions or trillions of stars, representing a sample size that would be adequate for almost any statistical analysis. The volume encompasses virtually every type of cosmic environment we could hope to study: young and old galaxies, dense galaxy clusters, and empty voids, regions of active star formation and cosmic graveyards where stellar birth has long since ceased. Moreover, the observable universe provides us with a natural laboratory for studying cosmic evolution. Because we see distant objects as they were in the past, we can observe the universe at different ages, simply by looking to different distances. The most distant galaxies show us cosmic conditions when the universe was young and different from today, while nearby galaxies reveal the mature cosmos in which we currently live. This temporal dimension transforms astronomy from a snapshot science into a time-lapse investigation of how the cosmos has changed and developed over billions of years. When we eventually arrive at our estimate of 40 quintillion stellar mass black holes, we must remember that this number applies specifically to the observable universe as we have defined it. We are counting the black holes that exist within approximately 46 billion light-years of Earth, those whose gravitational effects and formation histories fall within the scope of our cosmic horizon. Whether the true universe extends far beyond this boundary, and whether it contains vastly more black holes in unobservable regions, remains an open question that science cannot currently address. This uncertainty does not diminish the value of our investigation. The observable universe represents the entire portion of reality that is accessible to human knowledge and measurement. It encompasses everything that has ever influenced us or ever could influence us, everything whose existence can be confirmed through observation and analysis. Within this domain, our count of black holes provides genuine insight into cosmic demographics and the hidden population of gravitational remnants that surround us. It tells us about the universe we actually inhabit, the cosmic neighborhood in which Earth and humanity find themselves embedded. As we proceed to build the foundation for understanding how such a census is possible, we carry with us this clear definition of our scope and this appreciation for both the vastness of what we can study and the humbling reminder of what remains forever beyond our observational reach. Before we can meaningfully explore how scientists arrived at their estimate of black holes in the observable universe, we must first come to terms with the number itself. 40 quintillion. These words roll off the tongue easily enough, but they represent a quantity so vast that our minds, evolved to navigate a world of countable objects and manageable scales, simply cannot grasp their true meaning through intuition alone. This is not a failure of intelligence or education. It is a fundamental limitation of human psychology when confronted with numbers that exceed the boundaries of direct experience. Consider how we naturally understand quantity in daily life. You can instantly recognize the difference between 3 apples and 5 apples without counting. Your mind processes small numbers automatically, a skill that served our ancestors well when tracking family members, counting predators, or distributing limited resources. Even moderately large numbers remain somewhat accessible to imagination. 1,000 people filling a small theatre, 1,000,000 books in a major library, 1 billion seconds spanning roughly 32 years of life. These quantities challenge us, but we can still construct mental frameworks that give them meaning. But quintillion belongs to a different realm entirely. To understand what this word represents, we must first break it down systematically. In the American numbering system, each major unit represents a jump of 1,000. 1,000 is 10 to the 3rd power. 1,000,000 is 10 to the 6th power, or 1,000 thousands. 1 billion is 10 to the 9th power, or 1,000 millions. 1 trillion is 10 to the 12th power, or 1,000 billions. 1 quadrillion is 10 to the 15th power, or 1,000 trillions. And finally, a quintillion is 10 to the 18th power, or 1,000 quadrillions. When we say 40 quintillion black holes, we are speaking of 4 times 10 to the 19th power, a number that can be written as a 4 followed by 19 zeros. If you were to write this number in full, it would appear as 40,000 trillion, or alternatively, as 40 million trillion billion. Even these verbal representations fail to convey the true scale, because they require us to mentally multiply incomprehensibly large numbers by other incomprehensibly large numbers. Perhaps analogies can help where raw mathematics falters. Imagine you could somehow gather every grain of sand from every beach on Earth, not just the sand you can see on the surface, but every particle buried beneath, every grain that forms the hidden depths of coastal dunes and offshore deposits. Scientists estimate that Earth's beaches contain approximately 7 quintillion grains of sand. This means that the number of black holes in the observable universe exceeds the total number of sand grains on our entire planet by a factor of nearly 6. If you could assign one black hole to every grain of sand on Earth, you would still need 5 more complete Earths, each covered with beaches, to account for the full cosmic population. Here is another way to approach this scale. Consider time itself, measured in the smallest units that feel meaningful to human experience. A second passes quickly, but it is still noticeable, still distinguishable. How many seconds have elapsed since the universe began 13.8 billion years ago? The answer is approximately 400 trillion seconds. This means that the number of black holes in the observable universe exceeds the total number of seconds in all of cosmic history by a factor of 100,000. If a new second had begun with each tick of some cosmic clock at the moment of the Big Bang, and if that clock had been running continuously ever since, it would need to tick 100,000 times faster to equal the black hole count. Or consider this perspective from the world of human knowledge. The largest libraries on Earth contain approximately 50 million books. If we could somehow assign one black hole to each book in the world's greatest library, we would need to build 800 billion identical libraries to represent the full population. That would mean constructing more than 100,000 libraries for every person currently alive on Earth. Even then, the analogy barely captures the scale, because we are comparing discrete countable objects to a quantity that pushes against the very limits of numerical comprehension. These analogies serve a purpose beyond mere illustration. They demonstrate that 40 quintillion represents not just a large number, but a number so large that it belongs to the realm of cosmic demographics rather than earthly experience. It is a number that emerges naturally when we consider processes that operate across billions of years, affecting trillions of galaxies, each containing billions of stars. It reflects the accumulated result of stellar evolution operating throughout the entire observable universe across the full span of cosmic time. But here we must pause and establish an important principle for our journey together. These analogies and comparisons are meant to help you feel the magnitude rather than simply hear it. The goal is not to make 40 quintillion feel small or manageable, but to help you develop a respectful sense of its enormity. This number represents something profound about the universe we inhabit, something that changes our perspective on cosmic demographics and the hidden population surrounding us. However, we will not spend our time simply marveling at large numbers or drowning in analogies that ultimately fail to capture their true meaning. Instead, we are going to do something more valuable and more satisfying. We are going to build the chain of reasoning that makes this number not just believable, but inevitable. We will explore the physics of stellar evolution, the demographics of galaxies, and the computational methods that allow scientists to simulate billions of years of cosmic history. We will understand how black holes form, where they hide, and why their population has grown to such extraordinary levels. Only after we have constructed this foundation, only after we understand the scientific reasoning that supports such an estimate, will we return to contemplate what 40 quintillion black holes means for our understanding of the universe and our place within it. This approach honors both the magnitude of the number and the elegance of the science that makes it possible to calculate. It ensures that when we finally grasp the full implication of this cosmic census, We do so with genuine understanding rather than mere amazement at incomprehensible scale. To understand how the observable universe came to harbour 40 quintillion black holes, we must first understand how nature manufactures these mysterious objects in the first place. The story begins not with darkness and collapse, but with light and creation, in the nuclear furnaces of stars, where the elements of existence are forged through billions of years of patient burning. Every stellar mass black hole in the cosmos represents the final chapter of a stellar biography, the ultimate outcome of a negotiation between two fundamental forces that has played out across cosmic time in trillions of individual cases. Imagine a young star, perhaps 20 or 30 times more massive than our Sun, beginning its nuclear life in the dense heart of a stellar nursery. This newborn giant ignites its hydrogen fuel and begins what will become a millions of years long conversation between the inward pull of its own gravity and the outward pressure of nuclear fusion occurring in its core. Gravity, relentless and patient, seeks to compress the star's entire mass into the smallest possible space. Nuclear fusion, explosive and energetic, fights back by converting hydrogen into helium and releasing tremendous amounts of energy that push outward against gravitational compression. This stellar negotiation proceeds with remarkable stability for most of the star's lifetime. The fusion reactions in the core generate exactly the right amount of outward pressure to balance the inward gravitational pull, maintaining what astronomers call hydrostatic equilibrium. The star burns steadily, converting roughly 4 million tons of matter into pure energy every second through Einstein's famous equation relating mass and energy. This process continues year after year, century after century, maintaining a delicate balance that keeps the star shining and stable. But this equilibrium cannot last forever, because nuclear fuel is finite and gravity is eternal. As the star ages, it gradually converts hydrogen into helium in its core. Eventually, the central hydrogen supply becomes depleted, and the fusion reactions that have sustained the star begin to weaken. Without sufficient outward pressure to counteract gravity's inward pull, the core starts to contract. This contraction raises the core temperature, allowing new fusion reactions to begin. Helium nuclei begin fusing into carbon and oxygen, providing a temporary reprieve and allowing the star to continue shining. This pattern repeats itself through successive stages of stellar evolution. When helium is exhausted, the core contracts again until carbon fusion begins. Then oxygen fusion, then silicon fusion, each stage burning hotter and faster than the last. The star develops an onion-like structure, with shells of different fusion reactions proceeding simultaneously at different depths. Near the surface, hydrogen continues to burn. Deeper in, helium fuses into carbon. Deeper still, carbon burns to form oxygen and neon, while the very center processes silicon into iron. But iron represents a fundamental barrier in stellar nucleosynthesis. Iron nuclei are the most stable atomic nuclei in nature. Fusing iron requires energy input rather than releasing energy, which means that iron fusion cannot power a star or provide outward pressure to resist gravity. When the stellar core becomes dominated by iron, the star's fuel supply effectively reaches its end. The nuclear fires that have burned for millions of years begin to die, and gravity finally gains the upper hand in its ancient negotiation with fusion. What happens next unfolds with breathtaking speed. The iron core, no longer supported by fusion pressure, begins to collapse under its own immense gravity. In less than a single second, a region the size of Earth compresses to a sphere perhaps 20 kilometers across. The collapse is so violent and rapid that the core overshoots its equilibrium point, rebounding in a colossal explosion that astronomers call a supernova. For weeks or months, this single stellar explosion can outshine an entire galaxy containing billions of stars. But the supernova, spectacular as it appears, is actually a side effect of what happens to the collapsing core. Depending on the original mass of the star and the details of its evolution, this compressed core becomes one of two possible objects. If the core mass falls below approximately 2 to 3 times the mass of the Sun, it stabilizes as a neutron star, an exotic object composed entirely of neutrons packed together at nuclear density. A neutron star represents matter compressed to extraordinary extremes, where a teaspoon of material would weigh as much as a mountain on Earth. However, if the core mass exceeds this critical threshold, not even neutron degeneracy pressure can halt the gravitational collapse. The core continues to compress beyond the neutron star stage, shrinking past any known physical mechanism that might provide resistance. According to our current understanding of physics, this runaway collapse continues until the matter reaches infinite density at a geometric point called a singularity, surrounded by an event horizon beyond which nothing, not even light, can escape. A stellar mass black hole is born. This formation mechanism explains the origin of most stellar mass black holes in the universe, but it represents only one pathway among several. Stars rarely live in isolation. More than half of all massive stars exist in binary systems, gravitationally bound to a companion star. When massive stars exist in close binary pairs, their evolution becomes far more complex and interesting. The two stars can exchange mass through gravitational interaction, stripping material from each other's surfaces. They can merge during their lifetimes, combining their masses and altering their evolutionary paths. These binary interactions can change which stars end their lives as neutron stars versus black holes, and they can even create black holes from stars that would not have formed them in isolation. Binary evolution also affects the final properties of the black holes that form. A star that loses significant mass to a binary companion during its lifetime will leave behind a less massive remnant than it would have in isolation. Conversely, stars that accrete mass from companions or merge with them can produce more massive black holes than their original single-star evolution would have allowed. These binary pathways contribute to the diversity of black hole masses we observe and help explain why the actual population of stellar mass black holes differs from what we would predict based solely on single-star evolution. The formation of each stellar mass black hole represents the culmination of a unique stellar story, shaped by initial mass, metallicity, rotation, magnetic fields, and binary interactions. Yet despite this complexity, the fundamental process remains elegantly simple. Gravity's patient victory over nuclear fusion played out across millions of years of stellar evolution and concluded in a fraction of a second of catastrophic collapse. When we speak of counting black holes in the universe, we are actually discussing a diverse family of objects that share the fundamental property of gravitational collapse but differ dramatically in their masses, origins, and cosmic roles. Black holes do not come in a single variety, like identical coins in a collection. Instead, they form a complex population with distinct categories, each representing different formation mechanisms and evolutionary histories. Understanding this diversity is crucial for appreciating what our estimate of 40 quintillion black holes actually represents and why the question, how many black holes are there, requires careful specification of which type we mean. The black hole family portrait reveals three main categories, each occupying a different range of masses and playing a different role in cosmic evolution. At the lower end of the mass spectrum, we find stellar mass black holes, the direct descendants of massive stars that we explored in our previous discussion. These objects typically range from about 3 times the mass of the Sun up to perhaps 100 solar masses, though the exact upper limit remains a subject of ongoing research. Stellar mass black holes form through the core collapse mechanism we have already described, representing the final fate of stars, massive enough to overcome neutron degeneracy pressure during their death throes. At the opposite extreme of the mass spectrum reside the supermassive black holes, gravitational monsters that contain millions or billions of times the mass of the Sun. These colossal objects occupy the centers of galaxies, including our own Milky Way, where they exert profound influence over galactic structure and evolution despite their relatively small physical size. The supermassive black hole at the center of our galaxy, known as Sagittarius A star, contains approximately 4 million solar masses compressed into a region smaller than the orbit of Mercury. More distant galaxies harbour even larger supermassive black holes, some exceeding 10 billion solar masses and rivaling the total mass of all stars in smaller galaxies. Between these extremes lies a mysterious and sparsely populated middle ground occupied by intermediate mass black holes. These objects, if they exist in significant numbers, would contain hundreds to hundreds of thousands of solar masses, bridging the gap between stellar remnants and galactic giants. Intermediate mass black holes represent one of the most intriguing unknowns in modern astronomy, as their formation mechanisms remain poorly understood and confirmed detections remain rare and controversial. Some may form through the direct collapse of extremely massive stars in the early universe, while others might grow through the merger of smaller black holes in dense stellar environments. When we cite the number 40 quintillion black holes in the observable universe, we are referring specifically and exclusively to stellar mass black holes. This estimate emerges from calculations that track the formation and accumulation of stellar remnants across the entire history of cosmic star formation, from the first generation of stars that formed when the universe was young until the present day. The number includes black holes that formed billions of years ago and continue to drift silently through space, as well as those that formed more recently from the deaths of massive stars in contemporary galaxies. This focus on stellar mass black holes is both practical and necessary for several reasons. First, stellar formation and evolution are reasonably well understood processes that can be modelled with confidence using established physics. We know how stars form, how they evolve, and under what conditions they produce black holes rather than neutron stars. This knowledge allows scientists to create sophisticated computer simulations that follow the births and deaths of stellar populations across cosmic time, providing a solid foundation for population estimates. Second, stellar mass black holes represent by far the most numerous category in the cosmic census. While individual supermassive black holes are vastly more massive than their stellar cousins, they are also extraordinarily rare. Current estimates suggest that the observable universe contains perhaps 10 trillion supermassive black holes, one for each major galaxy. This may sound like a large number, but it represents less than 1/10,000,000th of 1% of the total black hole population by count, though a much more significant fraction by total mass. The rarity of supermassive black holes reflects both the rarity of galaxies compared to stars, and the fact that each galaxy typically hosts only one central supermassive black hole, though merging galaxies can temporarily contain multiple supermassive black holes until they eventually spiral together and coalesce. In contrast, each galaxy may contain millions or billions of stellar mass black holes distributed throughout its volume, the accumulated remnants of countless generations of massive stars that have lived and died since the galaxy formed. Intermediate mass black holes, if they exist in significant numbers, would fall somewhere between these extremes in both mass and abundance. However, their uncertain formation mechanisms and limited observational confirmation make them difficult to include in reliable population estimates. Current evidence suggests they are much rarer than stellar mass black holes, but potentially more common than supermassive giants, though the exact numbers remain highly speculative. The distinction between these categories matters profoundly for understanding cosmic evolution and structure formation. Stellar mass black holes represent a significant reservoir of ordinary matter, containing approximately 1% of all baryons in the observable universe locked away in gravitationally isolated remnants. They influence their immediate surroundings primarily through their gravitational effects on nearby stars and gas, occasionally revealing themselves when material falls into their gravitational wells and heats up enough to emit detectable radiation. Supermassive black holes, despite their small numbers, play a disproportionately important role in cosmic evolution. They regulate star formation in their host galaxies, drive powerful jets of material across hundreds of thousands of light years, and serve as the engines powering quasars and other active galactic nuclei that can be observed across billions of light years of space. Their influence extends far beyond their physical size, shaping the structure and evolution of entire galaxies and galaxy clusters. Perhaps most intriguingly, the origins of supermassive black holes remain one of the deepest mysteries in modern astrophysics. Unlike stellar mass black holes, whose formation through core collapse is well understood, supermassive black holes present a fundamental puzzle. How did objects containing millions or billions of solar masses form so early in cosmic history? Observations reveal fully formed supermassive black holes existing when the universe was less than 1 billion years old, yet conventional accretion processes would require much longer to build such massive objects from stellar mass seeds. To truly understand how 40 quintillion black holes came to populate the observable universe, we must fundamentally shift our perspective on cosmic time and stellar demographics. When we look up at the night sky and see the gentle glow of stars scattered across the darkness, we are witnessing only a small fraction of the stellar activity that has occurred throughout cosmic history. The universe we observe today, with its orderly galaxies and steady stellar populations, represents a mature and relatively quiet phase of cosmic evolution, quite different from the dynamic and productive epochs that dominated earlier eras. The universe has functioned as a vast star manufacturing facility for over 13 billion years, but its productivity has not remained constant throughout this immense span of time. Like any complex factory, cosmic star formation has experienced periods of intense activity and gradual decline, shaped by the availability of raw materials, the efficiency of assembly processes, and the changing conditions within the manufacturing environment. Understanding this variable productivity is crucial for counting black holes, because most of the massive stars that created today's black hole population formed and died billions of years ago, during cosmic epochs when star formation proceeded at rates far exceeding anything we observe in the contemporary universe. The story begins in the universe's youth, perhaps 1 to 3 billion years after the Big Bang, when cosmic conditions were dramatically different from today. Galaxies were smaller, more irregular, and more actively engaged in violent interactions and mergers. Gas was more abundant and less enriched with heavy elements, creating ideal conditions for rapid star formation. During this cosmic adolescence, the universe produced stars at rates roughly 10 times higher than we observe in modern galaxies. Vast stellar nurseries stretched across galactic disks, giving birth to massive stars that would live brief, brilliant lives before collapsing into the black holes we count today. This peak epoch of star formation, often called cosmic noon by astronomers, occurred when the universe was approximately 3 to 4 billion years old. During this era, the cosmic star formation rate reached its historical maximum, with new stars igniting throughout the observable universe at a pace that staggers the imagination. If we could somehow observe the entire cosmos during this period, we would see a universe ablaze with stellar birth, its galaxies glowing with the fierce blue light of young massive stars and the red emission of heated gas falling into gravitational wells to form the next generation of stellar systems. But this frenetic period of stellar productivity could not last indefinitely. Star formation requires abundant supplies of cold gas that can collapse under its own gravity to form dense stellar cores. As billions of years passed, several factors conspired to reduce the universe's star-forming capacity. The cosmic expansion itself played a role, as the stretching of space made it increasingly difficult for galaxy-scale gas reservoirs to maintain the densities required for efficient star formation. Stellar feedback also became more important over time, as the accumulated energy from supernovae, stellar winds, and other violent stellar processes began to heat and disperse the gas reservoirs that fuel star formation. Perhaps most significantly, the universe gradually consumed its gas supply through the star formation process itself. Each generation of stars converted hydrogen and helium into heavier elements, permanently removing raw materials from the cosmic inventory available for future star formation. While dying stars return some processed material to the interstellar medium, they lock away significant fractions of their original mass in long-lived stellar remnants like white dwarfs, neutron stars, and black holes. Over time, this steady consumption of gas has led to a universe where star formation proceeds at a much more leisurely pace than during the productive epochs of cosmic youth. Today's universe forms new stars at roughly 10% of the rate observed during cosmic noon. This represents a dramatic decline in stellar productivity that has profound implications for black hole demographics. The universe has essentially shifted from a phase dominated by stellar birth to one increasingly characterized by stellar death and the accumulation of stellar remnants. We live in an era when most of the stars that will ever exist have already formed, lived their lives, and contributed their heavy elements to the cosmic inventory. This historical perspective transforms our understanding of what it means to count black holes in the universe. We are not simply counting objects that exist now, but rather cataloguing the accumulated remnants of 13 billion years of stellar evolution. Most of the black holes in our 40 quintillion estimate formed from stars that died long before our solar system existed, during cosmic epochs when the universe was younger, more compact, and far more active in producing the massive stars that become black holes. This realization leads us to appreciate astronomy as fundamentally a demographic science, concerned not just with individual objects, but with populations, birth rates, death rates, and the statistical properties of cosmic constituents across vast scales of space and time. When we estimate the number of black holes in the observable universe, we are conducting a cosmic census that requires understanding how stellar populations have evolved throughout cosmic history, how different types of galaxies contribute to the overall stellar inventory, and how various physical processes have influenced the efficiency of black hole formation across different epochs and environments. The challenge resembles trying to understand the demographics of a vast ancient city by examining not just its current inhabitants, but all the people who have ever lived there throughout its entire history. We must account for changing birth rates, varying life expectancies, migration patterns, and the accumulation of memorial markers left by previous generations. In the cosmic case, those memorial markers are the black holes, neutron stars, white dwarf stars, and other remnants that preserve the legacy of stellar populations that formed and evolved during earlier phases of cosmic history. This demographic approach helps explain why the number 40 quintillion might initially seem surprisingly large compared to the stellar populations we observe in today's universe. We are not counting the descendants of current stars, but rather the accumulated remnants of all the massive stars that have ever existed throughout cosmic time, the vast majority of which formed during more productive epochs when the universe functioned as a far more efficient star manufacturing facility than the relatively quiet cosmos we inhabit today. As we delve deeper into the cosmic census of black holes, we encounter one of the most elegant and profound ways that the universe has changed its fundamental character over the course of cosmic history. This change involves something that astronomers call metallicity, a term that initially confuses many people because it means something quite different in astronomy than it does in everyday chemistry or materials science. Understanding metallicity and its evolution through cosmic time reveals how the universe literally changed its recipe for making stars and stellar remnants, gradually shifting the cosmic demographics of black hole formation in ways that profoundly influence our 40 quintillion estimate. In astronomy, the word metals refers not just to iron, copper, gold, and the other metallic elements familiar from chemistry, but to all elements heavier than helium. This peculiar usage reflects the historical origins of stellar spectroscopy, when early astronomers classified stellar compositions into just three broad categories: hydrogen, helium, and everything else. From an astronomer's perspective, carbon is a metal, oxygen is a metal, silicon is a metal, and even neon is a metal. This definition might seem arbitrary, but it captures something fundamental about cosmic element production. Hydrogen and helium were created during the first few minutes after the Big Bang, while virtually all heavier elements were forged later inside stars and dispersed through supernova explosions. When the universe was young, perhaps during its first billion years, stellar compositions were dramatically different from what we observe today. The earliest generation of stars, sometimes called population 3 stars, formed from gas that contained almost no metals at all, just the primordial hydrogen and helium created during Big Bang nucleosynthesis. These ancient stars, none of which survive today, lived brief lives and died in supernova explosions that scattered the first heavy elements into the interstellar medium. Subsequent generations of stars formed from gas increasingly enriched with these metals, gradually building up the cosmic abundance of elements heavier than helium through billions of years of stellar recycling. This metallicity evolution profoundly affects stellar evolution and the formation of stellar remnants in ways that are both subtle and important for understanding black hole demographics. Metals play a crucial role in stellar atmospheres, where they provide opacity that helps drive stellar winds. A star with higher metallicity loses more mass throughout its lifetime through these stellar winds, essentially shedding its outer layers more efficiently as it ages. This mass loss affects the final fate of the star when it reaches the end of its nuclear fuel supply, because the mass of the stellar core at the moment of collapse determines whether the star becomes a neutron star or a black hole. Consider two identical stars, each born with 25 times the mass of the Sun, but existing in different cosmic epochs. The first star forms in the early universe from gas with very low metallicity, containing perhaps 1/100th the metal content of stars forming today. The second star forms in a contemporary galaxy from gas enriched by billions of years of stellar nucleosynthesis. Despite their identical birth masses, these stars will evolve quite differently and leave behind different types of remnants. The metal-poor star from the early universe experiences relatively weak stellar winds throughout its lifetime because its atmosphere contains fewer heavy elements to drive mass loss. It retains most of its original mass as it progresses through successive stages of nuclear burning, maintaining a massive core when it finally exhausts its fuel supply. When core collapse occurs, this massive remnant easily exceeds the threshold for neutron star formation and becomes a black hole, perhaps retaining 15 to 20 solar masses in its final compact state. The metal-rich star from the contemporary universe tells a different story. Its atmosphere, rich in heavy elements, drives powerful stellar winds that steadily strip away its outer layers throughout its lifetime. By the time it reaches core collapse, it may have lost significant mass, leaving behind a less massive core that might form a neutron star rather than a black hole. Even if it does form a black hole, the remnant will likely be less massive than its low metallicity counterpart, perhaps containing only 8 to 12 solar masses. This metallicity effect means that the early universe was significantly more efficient at producing black holes than the contemporary cosmos. The first generations of stars formed from primordial gas were more likely to form black holes rather than neutron stars, and the black holes they formed were typically more massive than those produced by similar stars today. As cosmic metallicity gradually increased through stellar recycling, the universe slowly shifted toward producing more neutron stars and fewer, less massive black holes from stars of equivalent birth mass. This evolutionary trend has important implications for our cosmic black hole census. A significant fraction of the 40 quintillion stellar mass black holes in the observable universe formed during cosmic epochs when metallicity was much lower than today. These ancient black holes represent the remnants of stellar populations that had access to formation mechanisms no longer available in the metal-rich universe we inhabit. They are relics of cosmic youth, when the universe operated according to different demographic rules for stellar remnant production. The metallicity story also illustrates how cosmic evolution operates through multiple interconnected feedback loops. Early generations of massive metal-poor stars formed black holes efficiently, but their supernova explosions also enriched the interstellar medium with heavy elements. This enrichment gradually changed the conditions for subsequent star formation, making future generations less likely to form black holes, but more likely to produce the complex chemistry necessary for planetary systems and biological evolution. The universe essentially traded efficiency in black hole production for the chemical diversity that would eventually enable the emergence of complexity and life. Understanding metallicity evolution also helps explain why direct observations of black hole populations in the contemporary universe provide an incomplete picture of cosmic black hole demographics. Most of the black holes we can detect today formed relatively recently from metal-rich stellar populations, representing only the most recent chapter in a much longer story of black hole formation that extends back to cosmic epochs when the universe operated according to quite different rules. The vast majority of stellar mass black holes formed billions of years ago under conditions that no longer exist, making them invisible to most observational strategies, but crucial for understanding the complete cosmic census. This perspective reveals astronomy as a science that must grapple not just with the physics of individual objects, but with the historical evolution of cosmic processes across billions of years of changing conditions. Just as we begin to develop a clear picture of how individual massive stars create black holes through core collapse, nature reveals a complication that transforms our understanding completely. This complication is both elegant and profound, reshaping not only how black holes form, but also providing the key insight that makes modern black hole population studies possible. The complication is this: most massive stars do not live alone. They exist in gravitationally bound partnerships with other stars, engaged in cosmic dances that can last for millions of years and dramatically alter the fate that each star would have experienced in isolation. Binary star systems represent the rule rather than the exception among the massive stars that create stellar mass black holes. Current observations suggest that somewhere between 70 and 90% of stars massive enough to form black holes are born with at least one stellar companion, and many exist in even more complex multiple star systems. This statistic might initially seem like an interesting but secondary detail about stellar demographics, but it actually represents one of the most important factors governing black hole formation throughout cosmic history. Binary interactions can determine whether a massive star becomes a neutron star or a black hole, influence the mass of any resulting black hole, and even create black holes from stars that would not have formed them in isolation. The gravitational relationship between binary companions creates opportunities for interactions that have no equivalent in the evolution of isolated stars. When two massive stars orbit each other closely enough, they can exchange mass through various mechanisms, fundamentally altering their internal structure, evolutionary timeline, and ultimate fate. The details of these interactions depend sensitively on the orbital separation, the mass ratio between the two stars, and the stage of evolution at which the interactions become significant, creating a complex parameter space of possible outcomes that far exceeds the relatively straightforward evolution of single stars. Consider what astronomers call mass transfer, a process that can occur when one star in a binary system evolves faster than its companion and expands to fill its gravitational sphere of influence. Material from the expanding star begins to flow toward its companion, sometimes forming streams of gas that spiral inward like cosmic waterfalls. This transferred mass can change the internal structure of the receiving star, altering its nuclear burning rate, its lifetime, and its eventual fate. Meanwhile, the star losing mass may avoid certain evolutionary phases entirely, following a different path toward core collapse than it would have experienced in isolation. Even more dramatic are episodes of what astronomers term common envelope evolution, during which one star actually becomes embedded within the expanded outer layers of its companion. The embedded star spirals inward through the envelope material, depositing orbital energy that helps expel the surrounding gas and dramatically shrinks the binary system. These violent episodes can strip away most of the envelope mass from both stars, leaving behind a tight binary system of two compact cores that will evolve quite differently than either star would have in isolation. Some stars that might have become red supergiants and eventually formed relatively modest neutron stars instead become stripped cores that collapse into black holes. Binary systems can also experience complete mergers during their evolution, when orbital decay brings two stars into direct contact and they coalesce into a single, more massive object. Such mergers can create stars massive enough to form black holes even when neither original component would have reached the black hole threshold on its own. These merged stars often have unusual internal structures and evolutionary properties, following paths toward core collapse that differ significantly from the standard stellar evolution sequences derived from studying isolated stars. Perhaps most importantly for our cosmic census, binary evolution can create black holes through pathways that remain invisible to many traditional observational surveys. When a massive star in a binary system loses significant mass through stellar winds enhanced by tidal interactions, it may form a black hole that receives little or no ongoing mass transfer from its companion. Such systems can remain effectively invisible until some chance encounter or long-term orbital evolution brings new material within reach of the black hole's gravitational influence. These quiet binary systems represent a hidden population of black holes that can only be predicted through theoretical modeling rather than direct detection. The complexity introduced by binary evolution initially appears to make the problem of counting cosmic black holes much more difficult. Instead of tracking the straightforward evolution of isolated massive stars, we must now consider the intricate gravitational choreography of millions of different binary configurations, each evolving according to its own unique set of initial conditions and interaction histories. The parameter space becomes vast and seemingly intractable, involving not just stellar physics, but also orbital mechanics, tidal interactions, and the complex feedback between stellar evolution and binary dynamics. However, this complexity ultimately provides the key to modern black hole population studies. The same binary interactions that complicate individual predictions become statistically predictable when considered across large populations of stellar systems. Modern computational approaches can simulate the evolution of millions or billions of binary star systems, sampling the full range of possible initial conditions and following each system through its complete evolutionary history, from formation to final remnant. These population synthesis models transform physics into statistics, converting our understanding of stellar evolution and binary dynamics into quantitative predictions about black hole demographics. This computational approach represents a fundamental shift in how we study cosmic populations. Rather than trying to predict the fate of individual stars, which remains challenging given the complexity of binary interactions, we can reliably predict the statistical properties of entire stellar populations. We can estimate how many black holes should form in a galaxy of given mass and metallicity, how the black hole mass distribution should evolve over cosmic time, and how different assumptions about binary evolution affect the total census of compact remnants. The transition from individual stellar evolution to population-level statistics also reveals why binary stars represent not just a complication to be managed, but the great key that unlocks modern black hole demographics. Binary interactions create the diversity of evolutionary pathways necessary to populate the full range of black hole masses and formation mechanisms observed in nature. They provide the primary mechanism for creating black holes across a wide range of initial stellar masses and metallicities, ensuring that cosmic black hole formation remains efficient across different epochs and environments. This statistical approach, grounded in the physics of binary evolution, forms the foundation for the computational methods that produced our estimate of 40 quintillion stellar mass black holes in the observable universe. Now we arrive at the heart of our investigation, the elegant scientific methodology that transforms our understanding of stellar evolution, binary interactions, and cosmic history into a concrete estimate of black hole populations. This approach represents one of the most sophisticated applications of computational astrophysics to a fundamental question about the universe, combining multiple strands of astronomical knowledge into a single, comprehensive calculation that spans 13 billion years of cosmic time and encompasses the evolution of trillions of galaxies across the observable universe. The research that produced our estimate of 40 quintillion stellar mass black holes was published in the Astrophysical Journal, representing years of careful work to develop computational models that could reliably connect stellar physics to cosmic demographics. The fundamental approach involves coupling detailed stellar and binary evolution modeling with our best understanding of how galaxies form, evolve, and produce stars across cosmic history. This coupling creates a bridge between the microscopic physics of individual stellar systems and the macroscopic statistics of cosmic populations, allowing scientists to transform theoretical understanding into quantitative predictions about the contents of the observable universe. The methodology begins with what astronomers call population synthesis, a computational technique that simulates the evolution of millions of individual stellar systems from their formation in star-forming regions to their final fate as compact remnants. Each simulated star or binary system begins with initial properties drawn from observed distributions. Stellar masses following the initial mass function, binary orbital parameters reflecting measured statistics of stellar multiplicity, and metallicities appropriate for the cosmic epoch and galactic environment under consideration. The computer then follows each system through its complete evolutionary history, applying the physics of stellar structure, nuclear burning, mass loss, and binary interactions to determine what type of remnant each system will ultimately produce. This process generates what astronomers call a mass function, a concept that requires careful explanation because it differs fundamentally from simply making a list of individual objects. A mass function describes the statistical distribution of objects across different mass ranges, much like a demographic survey that tells us how many people exist in different age groups rather than providing the actual age of every individual person. For black holes, the mass function reveals how many black holes exist in each mass range, from the lightest stellar mass black holes barely exceeding 3 solar masses to the heaviest objects approaching 100 solar masses or more. The population synthesis calculations must be repeated for stellar populations forming at different cosmic epochs, because the initial conditions for star formation have changed dramatically throughout cosmic history. Stars forming in the early universe emerged from gas with very different metallicity than contemporary stellar populations, leading to different evolutionary outcomes and different black hole formation rates. Binary evolution proceeds differently in low metallicity environments, and even the initial mass function itself may have been different when the universe was young and the physical conditions in star-forming regions differed from those we observe today. The next crucial step involves integrating these stellar population results with our understanding of cosmic star formation history and galaxy demographics. This requires detailed modelling of how galaxies form and evolve across cosmic time, how their star formation rates change with redshift, and how the metallicity of star-forming gas gradually increases through stellar recycling. The calculations must account for the fact that different types of galaxies contribute differently to the cosmic census. Massive elliptical galaxies formed most of their stars in intense bursts early in cosmic history, while smaller spiral galaxies have maintained more gradual star formation rates extending to the present day. The computational models track star formation across the full range of galactic environments, from the dense centers of galaxy clusters, where star formation was quenched billions of years ago, to isolated, dwarf galaxies that continue forming stars today. Each environment contributes its own population of stellar mass black holes, formed under different conditions and at different epochs in cosmic history. The challenge lies in properly weighting each contribution according to the cosmic abundance of different galaxy types and their star formation histories. Perhaps most remarkably, this approach allows scientists to account for black holes that formed and died long before the present epoch. Unlike stars, which have finite lifetimes and eventually exhaust their nuclear fuel, black holes are essentially immortal on cosmic timescales. A black hole that formed from a massive star during the universe's youth continues to exist today, contributing to the current cosmic inventory even though the star that created it died billions of years ago. This means that today's black hole population represents the accumulated remnants of stellar evolution across the entire history of cosmic star formation. The integration over cosmic time requires careful modelling of how the observable universe has grown and evolved since the Big Bang. The calculations must account for cosmic expansion, which affects the volumes and densities involved in star formation, and for the changing physics of galaxy formation as the universe transitioned from its early phases, dominated by dark matter structure formation, to later epochs characterized by more gradual galactic evolution and declining star formation rates. When all these factors are properly combined and integrated across the full volume of the observable universe and the complete span of cosmic history, the calculations yield a remarkable result. Approximately 40 times 10 to the 18th power stellar mass black holes exist within the cosmic horizon accessible to our observation. This number emerges not from direct counting, which would be impossible given the invisibility of most black holes, but from the systematic application of well-established physics to the demographics of cosmic star formation across 13 billion years of universal history. The result carries profound implications beyond its sheer magnitude. These 40 quintillion black holes collectively represent approximately 1% of all ordinary matter in the observable universe, a surprisingly significant fraction that transforms our understanding of cosmic composition. This means that roughly 1% of all the protons and neutrons that constitute familiar atomic matter have been locked away in gravitationally isolated remnants, removed from further participation in cosmic evolution, except through their gravitational effects on surrounding matter. This fraction may sound modest, but it represents an enormous reservoir of mass that remains completely invisible to traditional astronomical observation. The black hole population constitutes a hidden component of cosmic baryonic matter that rivals in total mass many of the cosmic constituents we can observe directly, including all the stars currently shining in all the galaxies throughout the observable universe. It represents cosmic bookkeeping on the grandest possible scale, the universe's method of preserving and cataloguing its stellar history in a vast archive of dark, compact remnants. To fully appreciate the profound implications of our 40 quintillion black hole census, we must step back and place this number within the broader context of cosmic composition, examining what it means for roughly 1% of ordinary matter to be locked away in these invisible gravitational wells. This percentage might initially seem modest, but it represents something quietly revolutionary about our understanding of the universe and our place within it. To grasp why, we need to understand what astronomers mean by ordinary matter and how it fits into the much larger cosmic budget that governs the structure and evolution of everything we can observe. When we speak of ordinary matter in cosmology, we are referring specifically to what physicists call baryonic matter, the familiar stuff of atoms, molecules, planets, and stars. This includes all the protons and neutrons that make up atomic nuclei, along with the electrons that orbit around them to create the chemical elements we know from the periodic table. Ordinary matter forms everything we can touch, see with our eyes, or detect with traditional telescopes. The air we breathe, the ground beneath our feet, the sun that warms our planet, and all the distant stars and galaxies that populate our night sky. Yet here lies one of the most profound discoveries of modern cosmology. Ordinary matter, for all its familiarity and importance to our existence, represents only a tiny fraction of the total cosmic inventory. Current measurements indicate that baryonic matter constitutes approximately 5% of all the mass and energy in the observable universe. 5%. This means that everything we consider normal and familiar, from the smallest subatomic particles to the largest galactic clusters, from the simplest hydrogen atoms to the most complex biological molecules, represents less than 1/20th of cosmic reality. The remaining 95% of the universe consists of components that remain largely mysterious despite decades of intensive research. Roughly 27% takes the form of dark matter, a gravitationally active substance that neither emits nor absorbs electromagnetic radiation, but whose presence can be inferred through its gravitational effects on visible matter. Dark matter appears to provide the scaffolding upon which galaxies and larger cosmic structures form, yet its fundamental nature remains unknown. The remaining 68% consists of dark energy, an even more mysterious component that appears to be driving the accelerating expansion of space itself. Within this cosmic context, the revelation that stellar mass black holes contain approximately 1% of all ordinary matter takes on extraordinary significance. We are not discussing 1% of the total universe, which would be an incomprehensibly vast amount, but 1% of the small fraction that consists of familiar atomic matter. Yet even within these more modest boundaries, the implications are staggering. 1% of all baryonic matter represents a substantial cosmic component, roughly equivalent to the combined mass of all the gas between galaxies, or all the heavy elements produced by stellar nucleosynthesis throughout cosmic history. Consider what this means in practical terms. When you look up at the night sky and see the gentle glow of the Milky Way stretching across the darkness, you are observing perhaps the most prominent visible manifestation of ordinary matter in the universe. The combined light from hundreds of billions of stars reveals the location and structure of our galaxy, creating the impression that stars represent the dominant form of baryonic matter in the cosmos. Yet our black hole census reveals that invisible stellar remnants contain a mass comparable to a significant fraction of all the stars currently shining throughout the observable universe. This realization transforms our understanding of cosmic demographics in subtle but profound ways. The universe we observe through electromagnetic radiation, from radio waves to gamma rays, shows us only the active, energy-producing components of the cosmic inventory. Stars shine because they convert nuclear fuel into light and heat. Gas clouds glow when heated by stellar radiation or shocked by galactic collisions. Even exotic objects like neutron stars and white dwarf stars can be observed when they interact with surrounding matter or emit radiation from their hot surfaces. But black holes, representing 1% of all ordinary matter, remain almost entirely invisible to electromagnetic observation. They produce no internal light, reflect no external illumination, and reveal their presence only through the most subtle gravitational effects on nearby matter. This means that our traditional picture of the universe, built entirely from electromagnetic observations, systematically misses a significant component of cosmic baryonic matter. It is as if we have been trying to understand the demographics of a vast city by examining only the buildings with lights on, while remaining unaware of a substantial population living in darkened structures. The invisibility of this black hole population creates a fundamental asymmetry in our cosmic perspective. When we contemplate the universe through telescopic observation, we see a cosmos dominated by bright, active objects, stars burning nuclear fuel, galaxies blazing with stellar formation, quasars powered by supermassive black holes, accreting material at tremendous rates. This electromagnetic view suggests a universe where light dominates darkness, where energy production and radiation define cosmic activity and importance. Yet the black hole census reveals a different truth. The universe contains a vast, silent majority of gravitational remnants that participate in cosmic evolution only through their gravitational influence. These objects represent the accumulated legacy of 13 billion years of stellar evolution, a dark archive of cosmic history that preserves the memory of stellar populations that formed, evolved, and died long before our solar system existed. They are the universe's method of maintaining a permanent record of its stellar past, storing approximately 1% of all ordinary matter in gravitationally isolated vaults that will persist for time scales vastly longer than the current age of the cosmos. This perspective invites us to reconsider our relationship with the night sky and our understanding of cosmic abundances. The gentle starlight that has inspired human contemplation for millennia represents only the visible surface of a much deeper and more complex reality. Beneath that luminous surface lies a substantial foundation of dark matter in the form of stellar mass black holes, invisible to our eyes, but nonetheless real and influential in shaping the gravitational architecture of galaxies and the long-term evolution of cosmic structure. The realization that 1% of ordinary matter exists in this hidden form suggests that the universe is far more mysterious and complex than its visible appearance indicates, containing vast populations of objects and enormous reservoirs of mass that remain completely inaccessible to traditional observation, but nonetheless play crucial roles in cosmic evolution and structure formation. When most people imagine a black hole, the mental picture that emerges draws heavily from popular science documentaries, Hollywood films, and dramatic artistic renderings that emphasize the most visually spectacular aspects of these mysterious objects. This popular conception typically features a black hole surrounded by a brilliant accretion disk, a swirling maelstrom of superheated gas spiraling inward while glowing with intense X-ray radiation. Jets of plasma shoot outward from the poles at nearly the speed of light, creating lighthouse beams that can be detected across billions of light years. The black hole appears as a cosmic monster, actively devouring nearby stars and announcing its presence through violent displays of electromagnetic fireworks that illuminate the surrounding space. This dramatic image, while scientifically accurate for certain special cases, represents a profound misunderstanding of typical black hole behavior. The feeding, glowing, jet-producing black hole that dominates popular imagination is actually an extremely rare phenomenon, representing perhaps less than 1% of the total black hole population at any given time. The vast majority of black holes in the universe, including virtually all of the 40 quintillion stellar mass black holes in our cosmic census, exist in a completely different state: silent, invisible, and entirely inactive from an electromagnetic perspective. These quiet black holes drift through their host galaxies like gravitational ghosts, massive yet invisible, influential yet undetectable through traditional astronomical observation. They produce no light of their own, reflect no light from external sources, and generate no radio signals, X-ray emissions, or any other form of electromagnetic radiation that might reveal their presence to distant observers. They are the dark majority, the hidden population that constitutes the bulk of cosmic black hole demographics, yet remains almost entirely invisible to our telescopes and detectors. Understanding why invisibility represents the default state for black holes requires appreciating the specific conditions necessary for a black hole to become electromagnetically active. A black hole can only shine when it has access to material that can fall into its gravitational well and release energy through the accretion process. This material might come from a binary companion star that overflows its gravitational sphere of influence from interstellar gas and dust drifting through the galaxy, or from the tidal disruption of a star that ventures too close to the black hole's event horizon. However, space is remarkably empty on the scales relevant to individual stellar mass black holes. The typical black hole, with a gravitational sphere of influence extending only a few times the radius of the black hole itself, encounters very little material during its journey through the galaxy. Most black holes formed from the collapse of massive stars in relative isolation, without close binary companions that might provide ongoing fuel for accretion. Even those that originally formed in binary systems often find themselves alone after their companion stars evolve and die, leaving the black hole to wander through increasingly empty interstellar space. The density of interstellar gas in a typical galaxy is extraordinarily low by terrestrial standards, roughly equivalent to a few atoms per cubic centimetre. For a stellar mass black hole moving through such tenuous material at typical galactic velocities of hundreds of kilometres per second, the accretion rate remains far too small to generate detectable electromagnetic radiation. The black hole continues to exert its gravitational influence on nearby matter, but without sufficient material falling into its gravitational well, it remains as dark and silent as the vacuum of space itself. Even when a black hole does encounter sufficient material to begin accreting, the resulting active phase typically lasts for relatively brief periods compared to the black hole's total lifetime. A black hole that begins feeding on material from a disrupted star might shine brilliantly for months or years before exhausting the available fuel and returning to its quiet state. Binary systems where a black hole accretes from a companion star might remain active for millions of years. But even this represents only a tiny fraction of the billions of years that most black holes will exist in their host galaxies. This transient nature of black hole activity means that the dramatic feeding black holes we observe represent snapshots of brief active phases rather than typical black hole behavior. It is analogous to studying human demographics by focusing exclusively on people who happen to be running at the moment of observation. Such a survey would capture important information about human athletic capabilities, but would systematically miss the vast majority of people who spend most of their time in less energetic states. The quiet majority of black holes influences galactic evolution primarily through gravitational effects rather than electromagnetic processes. They contribute to the overall gravitational potential of their host galaxies, affecting the orbital dynamics of stars and the large-scale structure of galactic disks and halos. They can gravitationally perturb nearby stars, occasionally deflecting stellar orbits or participating in complex gravitational interactions that might eventually lead to stellar collisions or the ejection of stars from the galaxy entirely. Some quiet black holes reveal their presence only through extremely subtle observational signatures that require sophisticated analysis to detect. A black hole passing in front of a distant star might cause gravitational microlensing, briefly magnifying the star's apparent brightness in a way that reveals the presence and mass of the intervening dark object. A black hole orbiting a visible companion star might cause periodic Doppler shifts in the companion spectrum, revealing the gravitational influence of an unseen massive object even when no material is actively accreting onto the black hole. These indirect detection methods have allowed astronomers to identify several dozen stellar mass black holes in our own galaxy, but this represents only the tiniest fraction of the millions or billions of black holes that theoretical models predict should exist within the Milky Way. The vast majority remain completely undetectable with current technology, contributing to our galactic census only through statistical modeling rather than direct observation. This invisible majority helps explain how the cosmic black hole population can reach 40 quintillion without creating obvious observational signatures throughout the universe. Most of these objects drift silently through space, massive enough to influence local gravitational fields, but not active enough to announce their presence through electromagnetic radiation. They are the universe's dark archive, preserving the memory of stellar evolution in gravitationally isolated remnants that may persist long after all the stars currently shining have exhausted their nuclear fuel and faded into darkness. Given that the vast majority of stellar mass black holes remain invisible to direct observation, how do astronomers develop confidence in population estimates that reach into the quintillions? The answer lies in one of the most elegant aspects of modern astrophysics, the development of indirect detection methods that can reveal the presence of massive dark objects without requiring them to emit any light whatsoever. These techniques represent astronomy's evolution beyond its historical dependence on electromagnetic radiation, transforming the discipline into a more complete investigation of gravitational phenomena and cosmic demographics. The challenge of detecting invisible black holes has forced astronomers to become cosmic detectives, developing multiple independent investigative approaches that can converge on the same hidden population from different observational angles, like forensic investigators who might use fingerprints, DNA evidence, and eyewitness accounts to build a case. Astronomers have learned to combine various forms of indirect evidence to map the locations, masses, and properties of objects that produce no electromagnetic signatures themselves. The first and most direct of these approaches involves studying X-ray binary systems, where a black hole reveals its presence by actively accreting material from a nearby companion star. While we have established that most black holes remain quiet and inactive throughout their lifetimes, some find themselves in close binary partnerships that provide ongoing access to fuel for accretion. When material from a companion star falls toward a black hole, it forms an accretion disk that heats to temperatures of millions of degrees, glowing brilliantly in X-ray wavelengths that can be detected across thousands of light years. These X-ray binaries function like cosmic lighthouses, periodically illuminating black holes that would otherwise remain completely invisible. The X-ray emission provides not only evidence for the black hole's existence, but also information about its mass, spin, and accretion rate. By studying the timing of X-ray pulses, the spectral characteristics of the emission, and the orbital dynamics of the binary system, astronomers can determine whether the unseen object exceeds the maximum possible mass for a neutron star, confirming its identity as a black hole. However, X-ray binaries represent only the tip of the iceberg in terms of the total black hole population. Most black holes never experience significant accretion episodes during their lifetimes, so this detection method necessarily misses the vast majority of stellar mass black holes in any given galaxy. X-ray observations provide valuable information about black hole physics and binary evolution, but they offer limited insight into the total demographic census that includes quiet, isolated black holes. The second detection approach relies on gravitational dynamics, using the orbital motions of visible stars to infer the presence of unseen massive companions. When a star appears to orbit around an invisible object, astronomers can measure the star's orbital velocity and period to calculate the mass of its unseen partner through the same gravitational principles that govern planetary motion around the Sun. If this calculated mass exceeds the theoretical maximum for a neutron star, typically around 2 to 3 solar masses, the invisible object must be a black hole. This dynamical approach has proven particularly effective for studying black holes in our own galaxy, where individual stars can be monitored for years or decades to trace their orbital motion around invisible companions. Several of the most well-established stellar mass black holes known to astronomy were discovered through careful analysis of stellar dynamics rather than X-ray emission. These systems often involve black holes that accrete very little material from their companions, remaining electromagnetically quiet while still revealing their presence through gravitational influence. The dynamical method extends beyond individual binary systems to encompass the study of stellar motions near supermassive black holes at galactic centers. By tracking the orbits of stars around the center of the Milky Way over many years, astronomers have accumulated overwhelming evidence for a 4 million solar mass black hole at our galaxy's heart, despite the fact that this object produces relatively little electromagnetic emission compared to the active galactic nuclei observed in other galaxies. The third major detection approach exploits gravitational lensing, a phenomenon that emerges directly from Einstein's general theory of relativity. Massive objects warp the fabric of space-time around them, causing light rays to follow curved paths when passing nearby. This gravitational lensing effect can magnify and distort the apparent brightness and position of background stars when a black hole passes between the star and an observing telescope, creating a temporary brightening event that reveals both the presence and mass of the intervening dark object. Gravitational microlensing surveys monitor millions of stars simultaneously, searching for the characteristic brightening signatures that indicate when a massive dark object crosses the line of sight to a background star. The duration and amplitude of the lensing event provide information about the mass and distance of the lensing object, allowing astronomers to distinguish between different types of dark objects based on their gravitational signatures alone. This technique can detect black holes regardless of whether they produce any electromagnetic emission, making it sensitive to the quiet majority that remains invisible to other detection methods. Perhaps most remarkably, these three detection approaches often provide complementary information about the same black hole populations, allowing astronomers to build comprehensive pictures of black hole demographics that extend far beyond what any single method could reveal. X-ray observations identify actively accreting black holes and provide detailed information about their immediate environments. Dynamical studies reveal the presence of quiet black holes in binary systems and measure their masses with high precision. Gravitational lensing surveys can detect isolated black holes that have no binary companions and produce no electromagnetic activity whatsoever. The convergence of evidence from multiple independent detection methods provides the methodological foundation for confidence in large-scale population estimates when X-ray surveys, dynamical studies, and microlensing observations all point towards similar conclusions about black hole masses, formation rates, and spatial distributions. Astronomers can develop justified confidence in theoretical models that extrapolate these local measurements to cosmic scales. The 40 quintillion stellar mass black holes in our cosmic census represent not a single calculation, but the convergence of multiple observational approaches with sophisticated theoretical modeling of stellar evolution and galactic demographics across cosmic time. This multifaceted approach transforms black hole astronomy from a study of individual exotic objects into a systematic investigation of cosmic demographics, providing the observational foundation necessary to validate and refine the population synthesis models that produce our estimate of the total black hole census throughout the observable universe. To truly appreciate the scope and challenge of counting black holes throughout the observable universe, we need only look as close as our own cosmic neighborhood, where the Milky Way galaxy provides us with the most detailed and accessible laboratory for studying stellar mass black hole populations. Here, within the familiar spiral arms that sweep across our night sky, theoretical models predict the existence of somewhere between 100 million and 1 billion stellar mass black holes, the accumulated remnants of roughly 13 billion years of stellar evolution within our galactic home. Yet despite decades of intensive searching with increasingly sophisticated instruments, astronomers have conclusively identified only a few dozen of these predicted objects. This extraordinary disparity between theoretical expectation and observational reality within our own galaxy serves as both a humbling reminder of the limits of current astronomical detection methods and a powerful validation of the indirect approaches that make cosmic black hole censuses possible. The Milky Way, containing perhaps 400 billion stars and extending roughly 100,000 light-years in diameter, represents the most thoroughly studied galactic environment in the universe. We can observe individual stars within our galaxy, track their motions over years or decades, and detect electromagnetic radiation across the full spectrum from radio waves to gamma rays. Yet even in this uniquely accessible astronomical laboratory, the vast majority of predicted black holes remain completely invisible to our most sensitive instruments. The theoretical foundation for expecting such large numbers of stellar mass black holes in the Milky Way emerges from the same population synthesis modeling that produces cosmic scale estimates. Our galaxy has experienced a complex star formation history spanning billions of years, with different epochs characterized by varying star formation rates, stellar metallicities, and galactic structure. During its youth, the Milky Way likely formed stars at much higher rates than observed today, producing large populations of massive stars that would have evolved relatively quickly and left behind black hole remnants. Current models suggest that roughly 1 to 5% of all stars ever formed in the Milky Way were massive enough to potentially create black holes through core collapse. When combined with our understanding of binary evolution, metallicity effects, and stellar wind mass loss, these models predict that perhaps one in every few thousand stars that have ever existed in our galaxy should have produced a stellar mass black hole. Given the enormous number of stars that have formed and evolved in the Milky Way over cosmic time, this percentage translates to black hole populations measured in hundreds of millions or billions of objects. The observed population tells a dramatically different story. Astronomers have identified fewer than 24 stellar mass black holes in the Milky Way with high confidence, primarily through X-ray observations of accreting systems and dynamical studies of binary star systems where invisible massive companions influence the motions of visible stars. This number represents perhaps 1/10,000,000th of the theoretically predicted population, a discrepancy so vast that it might initially seem to invalidate either our theoretical understanding or our observational capabilities. The resolution of this apparent contradiction lies in understanding the profound selection effects that govern black hole detection. effects so strong that they render the vast majority of stellar mass black holes completely inaccessible to current observational methods. The few dozen black holes we have identified represent not a random sample of the total galactic population, but rather the tiny fraction that happen to exist under the very specific conditions required for electromagnetic detection. Most of the identified black holes in the Milky Way were discovered through X-ray observations during episodes of active accretion, when material falling into the black hole heats to millions of degrees and produces detectable radiation. However, these active accretion phases represent relatively brief episodes in the lifetime of most black holes. A typical stellar mass black hole might experience significant accretion for only a few thousand years out of its billion-year existence within. The galaxy, spending more than 99.9% of its lifetime in a completely quiet state that produces no detectable electromagnetic signature. The briefness of these active phases means that X-ray surveys capture only snapshots of black hole activity rather than comprehensive censuses of black hole populations. At any given moment, perhaps only 1 in 10,000 stellar mass black holes in the galaxy might be accreting sufficient material to produce detectable X-ray emission. The rest remain invisible, drifting silently through interstellar space with no ongoing fuel supply for accretion and no mechanism for announcing their presence through electromagnetic radiation. Even dynamical detection methods, which can identify quiet black holes through their gravitational effects on companion stars, face severe limitations when applied to galactic-scale surveys. These techniques require long-term monitoring of individual stellar systems to measure orbital motion and calculate the masses of unseen companions. Such detailed dynamical studies can only be conducted for relatively nearby stars within our local galactic neighborhood, and they require that the black hole exist in a binary system with a visible stellar companion that can be observed and monitored over multiple orbital periods. The majority of stellar mass black holes in the Milky Way likely exist in isolation, either because they formed from single stars or because their original binary companions have long since evolved and died. These isolated black holes can only be detected through gravitational microlensing events, which occur when a black hole happens to pass between Earth and a background star, temporarily magnifying the star's apparent brightness. However, such chance alignments are extremely rare, and even comprehensive microlensing surveys can detect only a small fraction of the total isolated black hole population. The profound mismatch between theoretical predictions and observational detections in our own galaxy provides crucial context for understanding cosmic black hole demographics. It demonstrates that the universe can contain enormous populations of objects that remain almost entirely hidden from direct observation, even when those objects possess substantial mass and exert significant gravitational influence on their surroundings. The 40 quintillion stellar mass black holes predicted throughout the observable universe are not purely theoretical constructs, but represent a natural extension of the hidden populations that we know must exist even within our own galactic neighborhood. This perspective transforms our understanding of the cosmos from one dominated by visible, electromagnetically active objects to one where substantial fractions of matter exist in dark, gravitationally influential forms that announce their presence only through the most subtle and indirect signatures. It suggests that much of the universe's demographic complexity remains hidden beneath the surface of what we can observe directly, accessible only through the sophisticated theoretical modeling and indirect detection methods that make modern black hole astronomy possible. Just as astronomers were developing increasingly sophisticated methods for detecting invisible black holes through their gravitational effects on nearby matter, nature provided an entirely new window into the hidden black hole population. This development represents one of the most profound advances in our understanding of the cosmos since Galileo first turned a telescope toward the heavens 4 centuries ago. It involves not the detection of light in any form, but rather the direct measurement of ripples in the fabric of space-time itself, disturbances that carry information about some of the most violent events in the universe directly to Earth across billions of light-years of space. Gravitational waves represent a fundamentally different type of astronomical observation, one that does not depend on electromagnetic radiation in any wavelength. Instead, these waves are actual distortions in space-time that propagate outward at the speed of light when massive objects undergo violent acceleration, much like ripples spreading across the surface of a pond when a stone is thrown into still water. The concept emerged from Einstein's general theory of relativity over a century ago, but the waves themselves remained a purely theoretical prediction until technological advances finally made their detection possible in the 21st century. The sources of detectable gravitational waves must involve enormous masses moving at tremendous speeds, creating accelerations so violent that they literally shake the fabric of reality itself. Among the most powerful such events in the universe are the final moments when two black holes, locked in a fatal gravitational spiral, merge into a single, more massive object. During these collisions, black holes containing tens of solar masses orbit each other hundreds of times per second, before finally coalescing in a burst of gravitational radiation that can exceed the power output of all the stars in the observable universe combined, though only for a fraction of a second. The detection of such waves requires instruments of extraordinary sensitivity, capable of measuring distortions in space-time smaller than 1/10,000th the width of a proton. The Laser Interferometer, gravitational wave observatory known as LIGO, accomplishes this seemingly impossible task using laser beams that travel back and forth along perpendicular arms extending several kilometers in length. When a gravitational wave passes through the detector, it slightly stretches space in one direction while compressing it in the perpendicular direction, causing minute changes in the time required for laser light to complete its journey along each arm. The first direct detection of gravitational waves occurred in September 2015, when LIGO recorded the merger of two black holes, each roughly 30 solar masses, located over 1 billion light-years from Earth. This historic observation opened an entirely new chapter in astronomy, providing the first direct confirmation that black holes of this size actually exist in nature, and that they can indeed merge through gravitational wave emission exactly as Einstein's theory predicted over a century earlier. Since that groundbreaking first detection, gravitational wave astronomy has rapidly matured into a powerful observational science. The LIGO detectors, joined by the European Virgo Observatory and other instruments around the world, have now recorded dozens of black hole mergers, creating a growing catalogue of events that provides unprecedented insights into black hole demographics, formation mechanisms, and cosmic evolution. This catalogue represents a remarkable achievement, as each detection provides direct, unambiguous evidence for the existence of multiple stellar mass black holes in distant galaxies. Perhaps most significantly for our cosmic census, gravitational wave detections validate the theoretical models that predict vast populations of stellar mass black holes throughout the universe. Each merger event detected by LIGO represents the final moment in the billion-year journey of two black holes that form from massive stars, evolved in isolation or binary systems, and eventually found each other through gravitational interaction. The observed merger rates allow astronomers to estimate how many black hole binary systems exist throughout cosmic space, providing an independent check on the population synthesis models that produce our 40 quintillion estimate. The black holes detected through gravitational wave astronomy represent what might be called the loud minority of the cosmic black hole population. These are the objects that, through chance encounters or long-term orbital evolution, find themselves paired with other compact objects in systems that eventually spiral together and merge. The gravitational waves they produce during their final moments announce their existence and properties to the entire observable universe, providing detailed information about their masses, spins, and distances that would be impossible to obtain through any other observational method. Yet for every black hole merger detected through gravitational waves, theoretical models suggest that thousands or millions of similar black holes exist in isolation, never encountering other compact objects and thus never producing detectable gravitational wave signals. These isolated black holes represent the vast quiet majority we have discussed throughout our journey, objects that remain invisible to electromagnetic observation and too widely separated to participate in merger events within the current age of the universe. The relationship between merging black holes and the total population resembles that between active galactic nuclei and the total population of supermassive black holes. Just as only a small fraction of supermassive black holes are actively accreting material and producing electromagnetic radiation at any given time, only a tiny fraction of stellar mass black holes participate in merger events that generate detectable gravitational waves. The rest remain gravitationally isolated, contributing to galactic dynamics and cosmic structure formation, but producing no signals that current technology can detect across intergalactic distances. Gravitational wave observations also provide crucial information about black hole formation mechanisms and evolutionary pathways. The masses and spins of merging black holes encode information about the stellar evolution processes that created them, the binary evolution that brought them together, and the environments in which they formed. By comparing observed merger rates and black hole properties with theoretical predictions, astronomers can refine their understanding of how efficiently different types of stellar populations produce black holes and how these objects evolve over cosmic time. The continued expansion of gravitational wave astronomy promises even greater insights into cosmic black hole demographics. Future space-based gravitational wave detectors will extend observations to much lower frequencies, enabling the detection of more massive black hole mergers and providing sensitivity to events throughout the observable universe. Ground-based detectors with increased sensitivity will detect merger events at greater distances and lower masses, building larger statistical samples that can constrain population models with ever greater precision. This growing gravitational wave census provides powerful validation for the indirect methods and theoretical modeling that produce cosmic-scale black hole population estimates. When multiple independent observational approaches point towards similar conclusions about black hole formation rates, mass distributions, and cosmic demographics, astronomers can develop justified confidence in estimates that extend far beyond what any single detection method could establish alone. As we continue building our understanding of cosmic black hole demographics, we encounter a mysterious and sparsely populated region of the black hole mass spectrum that has puzzled astronomers for decades and continues to challenge our most fundamental assumptions about how these objects form and evolve. Between the well-established populations of stellar mass black holes and supermassive giants lies what might be called the middle children of the black hole family, intermediate mass black holes containing hundreds to hundreds of thousands of solar masses. These objects occupy a curious gap in our cosmic census, appearing neither frequently enough to be considered a major population, nor rarely enough to be dismissed as irrelevant to cosmic evolution. The significance of intermediate mass black holes extends far beyond their modest numbers in current astronomical catalogues. They represent potential stepping stones in one of the deepest mysteries in modern astrophysics: how the universe managed to create supermassive black holes containing millions or billions of solar masses so early in cosmic history. Observations reveal fully formed supermassive black holes existing when the universe was less than 1 billion years old, Yet conventional accretion processes would require much longer to build such massive objects from stellar mass seeds. Intermediate mass black holes might provide the missing link, serving as more massive seeds that could grow into supermassive giants within the time constraints imposed by cosmic evolution. For many years, intermediate mass black holes existed primarily as theoretical possibilities rather than confirmed observational realities. Traditional electromagnetic observations revealed abundant evidence for stellar mass black holes through X-ray binaries and dynamical studies, while supermassive black holes announced their presence through powerful active galactic nuclei and the orbital dynamics of stars near galactic centers. But the intermediate mass range remained surprisingly empty, leading some astronomers to propose the existence of a fundamental mass gap in black hole demographics, a forbidden zone where black holes simply could not exist due to physical constraints on formation mechanisms. This apparent mass gap made theoretical sense from the perspective of stellar evolution. Stars massive enough to form black holes through core collapse typically produce remnants in the range of 3 to perhaps 50 solar masses, depending on their initial mass, metallicity, and binary evolution history. Larger stellar mass black holes would require progenitor stars so massive that they might be unstable during their main sequence lifetimes, or might lose so much mass through stellar winds that their cores could not grow large enough to exceed the neutron star threshold. Meanwhile, supermassive black holes seem to require entirely different formation mechanisms, perhaps involving the direct collapse of massive gas clouds in the early universe or the rapid growth of stellar mass seeds through super-Eddington accretion in dense environments. However, the advent of gravitational wave astronomy has begun to complicate this tidy picture, revealing black hole mergers that challenge our expectations about mass distributions and formation pathways. Several LIGO detections have involved black holes with masses approaching or exceeding 100 solar masses, pushing into the lower reaches of the intermediate mass range and suggesting that stellar evolution might be capable of producing more massive black holes than previously thought possible. These detections force astronomers to reconsider assumptions about stellar wind mass loss, binary evolution, and the maximum masses achievable through conventional stellar collapse mechanisms. The formation pathways for intermediate mass black holes, if they exist in significant numbers, remain subjects of active theoretical investigation and observational searching. Some might form through the merger of multiple stellar mass black holes in dense stellar environments like globular clusters, where gravitational interactions can bring compact objects together over millions of years. Others might emerge from the direct collapse of very massive stars in the early universe, when lower metallicity and different stellar formation conditions might have enabled the creation of stars hundreds of times more massive than anything observed in contemporary galaxies. Another intriguing possibility involves what astronomers call runaway stellar collisions in dense stellar systems, where repeated mergers of massive stars could create objects so large that they collapse directly into intermediate mass black holes without following standard stellar evolution pathways. These scenarios require very specific environmental conditions, including high stellar densities and relatively low metallicity, which might explain why intermediate mass black holes appear to be rare in contemporary galactic environments. The observational challenges associated with detecting intermediate mass black holes help explain their mysterious status in current astronomical catalogues. Unlike stellar mass black holes, which can be identified through X-ray emission when they accrete from binary companions, intermediate mass black holes typically exist in isolation without readily available fuel sources for ongoing accretion. Unlike supermassive black holes, which can be detected through their gravitational effects on entire galactic cores or through the powerful electromagnetic radiation produced by massive accretion disks, intermediate mass black holes possess insufficient mass to dominate their local gravitational environment and rarely encounter enough material to produce detectable electromagnetic signatures. Recent years have witnessed several tentative detections of intermediate mass black holes through various observational approaches, but most remain subjects of ongoing controversy and confirmation efforts. Some candidates have been identified through X-ray observations of ultraluminous X-ray sources in nearby galaxies, objects that produce more energy than typical stellar mass black hole systems, but less than supermassive active galactic nuclei. Others have been proposed based on the dynamics of globular clusters or the central regions of dwarf galaxies, where the motions of stars suggest the presence of concentrated dark mass in the intermediate range. The scientific importance of resolving the intermediate mass black hole question extends beyond simple demographic completeness. These objects might play crucial roles in cosmic evolution that remain hidden due to observational limitations. They could serve as the seeds for supermassive black hole formation, providing more massive starting points that can grow to billion solar mass scales within the age of the universe. They might influence the formation and evolution of globular clusters, stellar associations, and dwarf galaxies in ways that current models do not adequately account for. They could contribute to gravitational wave astronomy in frequency ranges that current detectors cannot access, but future space-based instruments might observe. The story of intermediate mass black holes exemplifies how scientific understanding progresses through cycles of theoretical prediction, observational testing, and conceptual refinement. What initially appeared to be a simple dichotomy between stellar mass and supermassive black holes has evolved into a more complex picture involving multiple formation mechanisms, environmental dependencies, and evolutionary pathways that continue to surprise and challenge astronomers. This ongoing investigation reminds us that the universe often proves more subtle and diverse than our theoretical frameworks initially suggest, requiring constant willingness to revise our understanding in response to new evidence. Before we return to contemplate the full implications of our 40 quintillion stellar mass black hole census, we must pause to consider a fascinating theoretical possibility that could fundamentally alter our understanding of black hole demographics and cosmic composition. This possibility involves a completely different class of black holes, objects that would predate the formation of the first stars by hundreds of millions of years, and whose existence would represent a direct fossil record of conditions in the extremely early universe. These hypothetical objects, known as primordial black holes, emerge not from stellar collapse, but from the gravitational collapse of density fluctuations during the first moments after the Big Bang, when the universe was far denser and more violent than anything we can observe today. The concept of primordial black holes represents one of the most intriguing intersections between cosmology and black hole physics, connecting the largest scales of cosmic structure formation with the most extreme manifestations of gravitational collapse. Unlike stellar mass black holes, which require the complex nuclear physics of stellar evolution and the precise conditions for core collapse, primordial black holes could form through purely gravitational processes during cosmic epochs, when the universe was young enough and dense enough for relatively small density perturbations to grow into gravitationally bound objects that immediately collapsed into black holes. During the first few 100,000 years after the Big Bang, the universe existed in a state dramatically different from the cosmic environment we observe today. Matter and radiation were coupled together at enormous densities and temperatures, creating conditions where even modest fluctuations in density could potentially grow large enough to overcome the pressure support provided by radiation and collapse directly into black holes. These density fluctuations might have arisen from quantum mechanical processes during cosmic inflation, from phase transitions in the early universe, or from other exotic physics operating during epochs when our understanding of fundamental forces becomes uncertain. The formation of primordial black holes would not require the billion-year stellar evolution processes that create conventional stellar mass black holes. Instead, regions of space containing slightly higher than average density could collapse almost immediately, forming black holes with masses determined entirely by the scale of the density perturbation and the cosmic conditions at the time of formation. Depending on when during cosmic history such collapse occurred, primordial black holes could potentially span an enormous range of masses, from tiny objects much lighter than asteroids to giants comparable to stellar mass black holes, or even larger intermediate mass objects. This broad possible mass range makes primordial black holes particularly intriguing for addressing some of the deepest mysteries in contemporary cosmology and astrophysics. Perhaps most significantly, primordial black holes have been proposed as candidates for dark matter, the mysterious gravitational component that comprises roughly 27% of the total cosmic mass energy budget, but has never been directly detected through electromagnetic or other non-gravitational interactions. If primordial black holes formed in sufficient numbers during the early universe, they could potentially account for all or part of the dark matter that appears to dominate cosmic structure formation. The appeal of primordial black holes as dark matter candidates stems from their fundamental gravitational nature. Unlike hypothetical dark matter particles that would require new physics beyond the standard model of particle physics, primordial black holes consist entirely of ordinary matter compressed to extraordinary density. They would interact gravitationally with all other forms of matter exactly as expected for dark matter, providing the gravitational scaffolding necessary for galaxy formation while remaining essentially invisible to electromagnetic observation. They would be dark matter in the most literal sense, gravitationally active ordinary matter that produces no light or other detectable radiation. However, this appealing possibility faces significant observational and theoretical constraints that limit the extent to which primordial black holes can contribute to cosmic dark matter. These constraints emerge from multiple independent lines of evidence, each probing different mass ranges and formation scenarios for primordial black holes. Observations of the cosmic microwave background radiation, which preserves information about density fluctuations in the early universe, place limits on how large early density perturbations could have been without producing observable signatures in the temperature patterns we measure today. Gravitational microlensing surveys, which can detect dark objects through their gravitational effects on background stars, constrain the abundance of primordial black holes in certain mass ranges by searching for the characteristic lensing signatures they would produce. If substantial numbers of primordial black holes existed with masses comparable to stellar remnants, they would occasionally pass between Earth and distant stars, creating temporary brightening events that microlensing surveys could detect. The relative rarity of such events places upper limits on how many primordial black holes can exist in these mass ranges. Additional constraints come from gravitational wave astronomy, which could potentially detect the merger of primordial black hole binaries if they existed in sufficient numbers. The merger rates and mass distributions observed by LIGO and other gravitational wave detectors can be compared with predictions for primordial black hole populations, providing another independent check on their possible abundance. Current observations suggest that conventional stellar mass black holes can account for the detected merger events without requiring significant contributions from primordial populations. Perhaps most importantly for our cosmic census, the various observational constraints make it extremely difficult for primordial black holes to account for all dark matter while remaining consistent with other astronomical observations. While primordial black holes might contribute to dark matter in certain mass ranges or under specific formation scenarios, they cannot serve as the complete explanation for cosmic dark matter without violating constraints from multiple independent observational approaches. This conclusion helps clarify and strengthen the meaning of our 40 quintillion black hole estimate. This number represents specifically the population of stellar mass black holes formed through conventional stellar evolution processes, the accumulated remnants of massive stars that formed, evolved, and died throughout the 13 billion year history of cosmic star formation. Even if primordial black holes exist in significant numbers, they would constitute an additional population beyond this stellar census, formed through completely different physical processes and representing a separate component of cosmic black hole demographics. The primordial black hole hypothesis thus serves as an intellectual detour that sharpens our understanding of the main storyline rather than contradicting it. Our cosmic census focuses on the gravitational archive of stellar evolution, the dark repository where the universe stores the memory of its star-forming history. Whether the universe also contains additional populations of primordial black holes formed through early universe physics remains an open and fascinating question, but one that does not diminish the significance of the vast stellar graveyard that surrounds us, invisible yet real, accounting for roughly 1% of ordinary matter throughout the observable universe. Having journeyed through the technical foundations of cosmic black hole demographics, we now arrive at a more contemplative understanding of what these 40 quintillion invisible objects represent in the broader context of cosmic evolution and meaning. Black holes, in this deeper perspective, reveal themselves to be far more than exotic gravitational anomalies or endpoints of stellar evolution. They function as the universe's most permanent and comprehensive archive, a vast distributed library that preserves the essential information about every massive star that has ever lived and died throughout the entire history of cosmic star formation. Consider what happens when a massive star reaches the end of its nuclear burning phases and undergoes core collapse. From one perspective, this represents the death and destruction of a stellar system that may have burned steadily for millions of years, converting hydrogen into heavier elements and radiating energy across interstellar space. The star's outer layers are expelled in a violent supernova explosion, dispersing processed nuclear material into the interstellar medium where it may eventually contribute to future generations of stars and planetary systems. But something fundamental about that star never disappears. The compressed remnant of its core, containing perhaps 10 to 50 times the mass of our Sun, becomes permanently preserved in the form of a stellar mass black hole. This preservation operates according to principles that differ profoundly from our everyday experience with creation and destruction. In terrestrial contexts, we are accustomed to cycles of growth and decay, construction and demolition, where complex structures eventually break down into simpler components that can be recycled into new forms. Even in stellar evolution, this pattern seems to apply. Stars form from collapsing gas clouds, burn through their nuclear fuel, and eventually return most of their processed material to the cosmic medium through stellar winds and explosive deaths. But black holes represent a fundamental exception to this cosmic recycling. Once matter crosses the event horizon and becomes part of a black hole's mass, it is effectively removed from further participation in cosmic evolution, at least on timescales comparable to the current age of the universe. The black hole preserves not only the mass of its progenitor star, but also, in some sense, the record of that star's existence and the cosmic epoch during which it formed and evolved. Each stellar mass black hole serves as a permanent monument to a specific moment in cosmic history, a gravitational fossil that maintains its essential properties for time scales that dwarf the age of the universe itself. This archival function takes on profound meaning when we consider the 40 quintillion stellar mass black holes scattered throughout the observable universe. They represent the cumulative record of 13 billion years of cosmic star formation, preserving samples from every major epoch of galactic evolution and stellar nucleosynthesis. Black holes formed in the early universe, when metallicity was low and massive stars could grow to enormous sizes, maintain their distinctive masses and properties as permanent records of those ancient cosmic conditions. More recently formed black holes preserve information about stellar evolution in metal-rich environments, serving as benchmarks for understanding how cosmic chemistry has evolved over time. The universe, viewed through this lens, emerges not merely as a dynamic system of ongoing creation and destruction, but as a careful bookkeeper that maintains permanent records of its own developmental history. Nothing that achieves sufficient mass and density ever truly disappears from the cosmic inventory. Instead, it becomes transformed and preserved in forms that may be invisible to electromagnetic observation, but remain gravitationally real and permanently influential in cosmic evolution. This perspective carries particular resonance for mature audiences who have witnessed the cycles of creation and preservation that characterize human institutions and individual lives. Just as libraries preserve the intellectual achievements of past generations, museums maintain artifacts from historical periods, and traditions carry forward the essential insights of earlier cultures. The universe appears to operate according to similar principles of preservation and memory. The cosmos does not simply discard the products of its stellar creativity, but maintains them in archived forms that continue to participate in gravitational interactions and structural evolution. The philosophical implications extend beyond simple preservation to encompass questions about cosmic purpose and meaning. The fact that the universe naturally develops mechanisms for storing and maintaining records of its own history suggests a deep connection between physical processes and information preservation that transcends our usual categories of conscious and unconscious, deliberate and accidental. The cosmos appears to be inherently memorial, built according to principles that ensure important information about its developmental history remains accessible, even if only through gravitational archaeology rather than direct observation. Black holes also represent a form of cosmic patience that challenges human perspectives on time and permanence. While individual human lives unfold over decades, and even human civilizations rise and fall over centuries or millennia, stellar mass black holes maintain their essential properties across timescales that span hundreds of billions or even trillions of years. They are among the most permanent structures in the universe, outlasting not only the stars that created them, but also the galaxies in which they formed, and potentially even the cosmic expansion that will eventually separate them from all other matter in the observable universe. This extraordinary longevity transforms our understanding of cosmic priorities and values. In a universe where most processes operate through cycles of formation and dissolution, where even the longest-lived stars eventually exhaust their fuel and fade into darkness, black holes represent islands of stability that preserve essential information across cosmic epochs. They suggest that the universe places fundamental importance on maintaining records of its creative achievements, ensuring that the mass and energy invested in stellar evolution never simply vanishes, but remains permanently catalogued in forms that will persist long after all other traces of cosmic history have been erased by expansion and entropy. From this contemplative perspective, the 40 quintillion stellar mass black holes in our cosmic census represent not just a demographic statistic, but a profound statement about the nature of existence itself. They reveal a universe that operates according to principles of both creativity and conservation, one that generates new forms of complexity and beauty while simultaneously ensuring that the essential achievements of cosmic evolution are preserved for indefinite future reference. In the darkness between galaxies, scattered throughout space in forms invisible to our eyes, lies the universe's most comprehensive and permanent library, a gravitational archive that maintains the memory of stellar creation across all of cosmic time. As we stand at the threshold of unprecedented technological capabilities in astronomy, We find ourselves poised to transform our cosmic black hole census from a primarily theoretical exercise based on stellar evolution modelling into a comprehensive observational survey that could directly measure the properties and distributions of these invisible populations throughout the local universe. The coming decades promise to usher in an era of black hole astronomy that will make our current detection capabilities seem as primitive as Galileo's first telescope appears to modern observers, opening new windows into the hidden demographics of cosmic gravitational remnants and potentially revolutionizing our understanding of stellar evolution, galactic structure, and cosmic composition. The transformation will emerge from multiple converging technological advances, each addressing different aspects of the black hole detection challenge and collectively providing the tools necessary to conduct direct surveys of populations that currently exist only as statistical predictions in computer models. Perhaps most immediately promising is the revolution in astrometric precision exemplified by the European Space Agency's Gaia mission, which has already demonstrated the ability to measure stellar positions and motions with unprecedented accuracy across our local galactic neighbourhood. Gaia's extraordinary precision in measuring stellar positions opens the door to a detection method that could provide direct model-independent measurements of black hole masses and spatial distributions throughout the Milky Way. When a dark, massive object like a stellar mass black hole passes between Earth and a background star, it produces not only the temporary brightening signature of gravitational microlensing, but also a subtle deflection in the apparent position of the background star. This astrometric microlensing effect provides information about both the mass of the lensing object and its distance from Earth, allowing astronomers to distinguish definitively between different types of dark objects and measure their properties with remarkable precision. The power of astrometric microlensing lies in its ability to detect and characterize isolated black holes that would remain completely invisible to all other current detection methods. Unlike X-ray observations, which require active accretion, or dynamical studies, which require visible binary companions, astrometric microlensing can identify any dark massive object that happens to pass near the line of sight to a catalogued background star. Since Gaia has measured precise positions for over 1 billion stars in our galaxy, it provides an enormous grid of potential background sources for microlensing surveys, dramatically increasing the probability of detecting chance alignments with dark objects. Current estimates suggest that astrometric microlensing surveys using Gaia quality data could detect dozens to hundreds of isolated stellar mass black holes within our local galactic neighbourhood over the next decade. Each detection would provide direct measurements of black hole mass and distance, allowing astronomers to begin constructing the first observational mass function for the local black hole population. These measurements would provide crucial tests of the population synthesis models that currently provide our only estimates of cosmic black hole demographics, either confirming theoretical predictions or revealing discrepancies that would require revisions to our understanding of stellar evolution and black hole formation. Even more revolutionary prospects await with the development of space-based gravitational wave astronomy, led by the Laser Interferometer Space Antenna mission, scheduled for launch in the 2030s. LISA will operate as a constellation of 3 spacecraft separated by millions of kilometers, using laser interferometry to detect gravitational waves at much lower frequencies than ground-based detectors like LIGO can access. This frequency range opens an entirely new window into black hole demographics, enabling the detection of mergers involving more massive black holes across much greater cosmic distances. LISA's sensitivity to low-frequency gravitational waves will allow it to detect the inspiral phase of black hole mergers long before the final coalescence that produces signals detectable by ground-based instruments. This extended observation window will provide detailed information about black hole masses, spins, and orbital evolution that could reveal the formation histories and evolutionary pathways of merging systems. More importantly for cosmic demographics, LISA will be sensitive to black hole mergers throughout much of the observable universe, potentially detecting thousands of events per year and building comprehensive statistical samples of merging black hole populations across cosmic time. The next generation of ground-based gravitational wave detectors promises even greater sensitivity and reach. The proposed Einstein telescope, designed as an underground facility in Europe, would improve upon current LIGO sensitivity by an order of magnitude, extending detections to much greater distances and much smaller black hole masses. Similarly, the Cosmic Explorer concept envisions ground-based detectors with 40-kilometer arm lengths, providing sensitivity improvements that would make black hole merger detections routine throughout the observable universe. These advances in gravitational wave astronomy represent more than simply building better telescopes. They constitute a fundamental expansion of human sensory capabilities, allowing us to directly observe space-time disturbions produced by some of the most violent events in cosmic history. Just as the development of radio astronomy in the 20th century revealed previously invisible cosmic phenomena and transformed our understanding of galactic structure and cosmology, gravitational wave astronomy is opening an entirely new channel of information about the universe that operates independently of all forms of electromagnetic radiation. The convergence of advanced astrometric surveys and expanded gravitational wave capabilities will create unprecedented opportunities for what astronomers call multi-messenger astronomy, where the same cosmic events or populations are studied through multiple independent observational channels. Black hole demographics will benefit enormously from this multifaceted approach, as astrometric microlensing provides information about isolated black holes, while gravitational wave detections reveal the properties of merging systems, together building comprehensive pictures of black hole populations that neither approach could achieve alone. Looking further ahead, even more ambitious concepts are under consideration, including gravitational wave detectors based on pulsar timing arrays that use the entire galaxy as a detection instrument, and space-based interferometers with baseline separations measured in astronomical units rather than mere millions of kilometers. These future capabilities would extend gravitational wave sensitivity to even lower frequencies and greater distances, potentially detecting the gravitational wave background produced by all black hole mergers. Throughout cosmic history, this expanding observational toolkit promises to transform our 40 quintillion black hole census from an elegant theoretical calculation into a directly measured cosmic demographic survey, revealing the actual distribution, properties, and evolutionary history of the universe's vast population of invisible gravitational remnants. Now, after our extended journey through stellar evolution, binary dynamics, cosmic demographics, and the observational challenges of detecting invisible populations, we return to the central question that began our investigation with a deeper appreciation for both its complexity and its answer. The estimate of approximately 40 quintillion stellar mass black holes throughout the observable universe now carries the weight of understanding rather than mere astonishment at incomprehensible numbers. We have traced the scientific reasoning that connects stellar physics to cosmic demographics, explored the multiple independent lines of evidence that support such extraordinary population estimates, and examined the technological frontiers that may soon transform theoretical predictions into direct observational surveys. Yet our journey toward understanding would be incomplete without acknowledging the inherent uncertainties that accompany any attempt to conduct a cosmic census of objects that remain largely invisible to direct observation. The 40 quintillion estimate emerges from sophisticated computational models that necessarily incorporate assumptions about physical processes, cosmic history, and stellar demographics that remain subject to ongoing refinement and revision. Each assumption carries its own range of uncertainty, and these individual uncertainties combine in complex ways to produce a final population estimate that should be understood as representing the most probable value within a potentially substantial range of possibilities rather than a precise count that could never be revised. Consider the fundamental assumptions that underlie our cosmic black hole census. The population synthesis models that produce the 40 quintillion estimate must make assumptions about the cosmic star formation history, drawing on observational surveys of distant galaxies to reconstruct how rapidly different types of galaxies formed stars during different epochs of cosmic evolution. These observations necessarily involve substantial uncertainties, particularly for the earliest epochs of cosmic history, when galaxies were smaller, more irregular, and more difficult to observe with current telescopes. Small changes in assumed star formation rates during critical periods of cosmic history could significantly alter the total number of massive stars that have ever existed, and thus the number of black holes they would have produced. The models must also make assumptions about stellar evolution and the conditions under which massive stars produce black holes rather than neutron stars. These assumptions involve detailed stellar physics, including nuclear burning rates, stellar wind mass loss, and the complex interactions that occur in binary star systems. While our understanding of these processes has advanced considerably through decades of theoretical development and observational testing, significant uncertainties remain, particularly regarding the evolution of very massive stars and the efficiency of various binary interaction mechanisms that can alter stellar masses and evolutionary outcomes. Metallicity evolution represents another crucial source of uncertainty in cosmic black hole demographics. The models must assume how quickly the heavy element content of star-forming gas increased throughout cosmic history as successive generations of stars processed primordial hydrogen and helium into carbon, oxygen, silicon, iron, and other elements that affect stellar evolution. Different assumptions about metallicity evolution lead to different predictions about stellar wind strengths, mass loss rates, and ultimately the masses of stellar remnants produced during different cosmic epochs. Since metal-poor stars from the early universe may have been more efficient at producing black holes, uncertainties in cosmic metallicity, evolution translate directly into uncertainties in black hole formation rates. The binary fraction represents yet another significant uncertainty. The models must assume what fraction of massive stars exist in binary systems that can alter their evolutionary paths through mass transfer, common envelope evolution, and merger processes. While observational surveys suggest that most massive stars do exist in binary systems, the exact percentage remains difficult to determine observationally, and the range of possible binary interactions creates an enormous parameter space that affects black hole formation rates and mass distributions. Despite these substantial uncertainties, the fundamental conclusion about cosmic black hole demographics appears robust against reasonable variations in the underlying assumptions. Different groups of researchers using different stellar evolution codes, different assumptions about cosmic star formation history, and different approaches to modeling binary interactions have consistently arrived at population estimates that fall within the same order of magnitude. While the precise number might be 20 quintillion rather than 40 quintillion, or perhaps as many as 100 quintillion, the basic insight remains unchanged. Stellar mass black holes represent a substantial and previously underappreciated component of cosmic ordinary matter. This robustness reflects the fact that our estimate does not depend critically on any single assumption or observation, but emerges from the convergence of multiple independent lines of evidence and reasoning. Stellar evolution theory, binary population synthesis, cosmic star formation observations, and gravitational wave detections all point toward similar conclusions about the cosmic abundance of stellar mass black holes. Even if individual components of this analysis require revision, the overall picture appears sufficiently well-grounded to support confidence in the general magnitude of cosmic black hole populations. More importantly, the specific numerical value of our cosmic black hole census matters less than the deeper revelation it represents about the nature of the universe we inhabit. Whether 40 quintillion or some other number in the same approximate range, these population estimates reveal that the cosmos contains vast reservoirs of matter in forms that remain completely invisible to traditional astronomical observation. They demonstrate that our electromagnetic view of the universe, spectacular and informative as it has proven to be, systematically misses substantial fractions of the cosmic inventory that nonetheless play important roles in gravitational dynamics and cosmic evolution. The methodology that produces our black hole estimate also represents a triumph of theoretical astrophysics, demonstrating how sophisticated computational modeling can bridge the gap between detailed physics and cosmic scale demographics. The ability to simulate the evolution of millions of stellar systems across billions of years of cosmic time, incorporating complex binary interactions and environmental effects, represents one of the most ambitious applications of computational science to fundamental questions about cosmic composition and evolution. Even if future observations require significant revisions to our current population estimates, the scientific framework that makes such estimates possible will continue to provide the foundation for understanding how local stellar physics connects to global cosmic demographics. The 40 quintillion stellar mass black holes in our current census represent not a final answer, but the first reliable attempt to count one of the universe's most abundant yet invisible populations, opening new questions about cosmic evolution, galactic dynamics, and the hidden complexity of the cosmos that surrounds us. As our exploration draws to its close, we return to that simple moment with which we began. You standing beneath a clear night sky, gazing upward at the familiar patterns of starlight that have guided and inspired humanity throughout our entire history on this planet. But now, armed with the knowledge we have gathered together, that peaceful moment carries a profoundly different meaning. The gentle glow of distant stars no longer represents the primary contents of the universe, but rather the luminous minority, the visible surface of a far deeper and more complex cosmic reality that extends infinitely beyond what our eyes can perceive. Above you, scattered throughout the space between those welcoming points of starlight, drift 40 quintillion invisible companions. They are the silent witnesses to 13 billion years of cosmic evolution, the gravitational archives where the universe stores the memory of every massive star that has ever lived and died since the first stellar nurseries began their ancient work of converting hydrogen into light, heat, and the chemical elements necessary for complexity and life. These black holes represent not emptiness or destruction, but the cosmos's most permanent form of preservation, ensuring that the essential achievements of stellar creativity remain forever catalogued in gravitational vaults that will outlast the stars themselves. This revelation transforms our understanding of cosmic demographics from a picture dominated by bright, active objects to one where the majority of matter exists in quiet, invisible forms that participate in cosmic evolution primarily through their patient gravitational influence. The universe emerges not as an empty theatrical stage, decorated with occasional brilliant performances by stars and galaxies, but as a vast community where luminous lives and dark remnants exist in intimate partnership, each contributing to the gravitational architecture that enables continued cosmic development and the eventual emergence of complexity, chemistry, and consciousness. The 40 quintillion black holes surrounding us represent roughly 1% of all ordinary matter in the observable universe, a substantial cosmic component that remained completely hidden until sophisticated theoretical modelling and indirect detection methods revealed its presence. This invisible population rivals in total mass many of the cosmic constituents we can observe directly, yet it announces itself only through the most subtle gravitational signatures and the occasional violent merger events that produce ripples in space-time itself. It is dark matter in the most literal sense, familiar atomic matter compressed to extraordinary density and rendered invisible by the very strength of its own gravitational field. Understanding the true demographics of our cosmic neighbourhood does not diminish our significance or reduce the wonder of existence. Rather, it contextualizes human life and consciousness within a universe that proves far more interesting, complex, and richly populated than its visible appearance initially suggests. We are not isolated accidents clinging to a small planet in a vast empty cosmos, but participants in an ongoing cosmic story that has been carefully preserving the records of its own creative development for billions of years before our solar system even existed. The knowledge that 40 quintillion stellar mass black holes surround us carries a quality of cosmic companionship that extends our sense of connection far beyond the familiar boundaries of Earth and its immediate astronomical neighbours. These invisible objects represent the remnants of stellar civilizations, if we may use that term, that preceded us by billions of years. Each black hole preserves the essential mass and energy of a massive star that once burned brightly, synthesized heavy elements, and contributed to the cosmic chemistry that would eventually enable rocky planets, complex molecules, and living systems like ourselves. In contemplating this hidden population, we discover that the universe operates according to principles that mirror some of our deepest human values: the importance of memory, the preservation of achievement, and the patient maintenance of libraries that store essential information for future reference. The cosmos appears to be inherently memorial, built according to natural laws that ensure important records of creative activity are maintained across timescales that dwarf individual human lifetimes, entire civilizations, and even the evolutionary history of our species. This perspective invites us to reconsider our relationship with cosmic time and our place within the unfolding story of universal development. While human concerns naturally focus on timescales measured in years, decades, or centuries, the black holes above us operate according to temporal rhythms measured in billions or trillions of years. They remind us that the universe itself maintains perspectives and priorities that extend far beyond immediate circumstances, working according to patterns of patience and preservation that offer profound lessons about endurance, significance, and the long-term consequences of creative activity. The night sky, viewed with this deeper understanding, becomes not a source of existential loneliness or cosmic insignificance, but a gentle reminder that we exist within a universe that has been carefully tending its achievements and maintaining its memory for eons before our arrival, and will continue doing so long after our departure. The darkness between stars is not empty, but filled with the gravitational presence of objects that testify to the cosmos's commitment to preserving the products of stellar creativity and maintaining permanent records of evolutionary achievement. As you prepare for rest, carried towards sleep by the rhythm of these cosmic contemplations, let the knowledge of 40 quintillion invisible companions provide not anxiety about incomprehensible scales, but comfort in the recognition that the universe operates according to principles of careful stewardship and patient preservation. Above every sleeping city, throughout every peaceful night, the sky holds both the light we can see and the histories we can only infer through sophisticated science and mathematical modelling. Yet both forms of cosmic presence are equally real, equally significant, and equally deserving of our wonder and appreciation. The gentle starlight that has inspired countless generations of human contemplation represents only the visible introduction to a far grander cosmic story, one in which darkness and light, creation and preservation, the seen and unseen work together to maintain the ongoing project of universal development and the slow emergence of complexity, consciousness, and understanding, from the patient interplay of gravity, time, and the fundamental forces that govern all existence.